friends, well-wishers, as well as those who join us on Facebook Live or on Instagram. Maybe there's some posting going on. My name is Michael Christie. I'm the primary instructor for Senior Design, and yeah, happy to be your Master of Ceremonies today. Before we roll into the program itself and tell you a little bit about the program, I'd like to invite the Dean of the College of Engineering, Dr. Puello, to the stage to give you a welcome on behalf of the college. Dr. Puello.
I think I speak loud enough where I probably don't need a microphone, but I do need my notes here. But thank you for introducing me, Jack Puello. I'm the relatively new Dean of the College of Engineering and Computing. I believe it's week 11 now, but it's my pleasure to greet our students, faculty, staff, industry partners, and other guests today to this event. You know, biomedical engineering represents one of the most inspiring intersections of science, medicine, and innovation. It truly embodies what I like to call the pipeline, from knowledge to discovery to innovation, where studies are used to gather facts and data, and then subsequent analysis might lead to that aha moment, where some of these new findings are turned into discovery that generates useful products, technology, or processes that solve real problems to benefit our society. Ultimately, that's what we're trying to do. Every day, biomedical engineers like you improve lives. You develop these innovations, including medical personnel, including helping medical personnel diagnose disease earlier, restore mobility, advance personalized medicine, and create solutions that were unimaginable just maybe a generation ago, maybe even just a few years ago. From medical imaging and artificial intelligence and regenerative medicine, maybe even an AI diagnostic algorithm to hear heart sounds. Does that sound familiar? One of our faculty. Or maybe a novel device called Cervexa for early risk assessment of preterm labor. Does that one sound familiar?
Yes.
From last year's Senior Design, last spring's winter. Your profession is transforming healthcare and improving the quality of life for people around the world. The work you're presenting today is part of that larger mission. Behind every design, every experiment, every prototype, and every approach that you take to analyze data, that's a potential to make something meaningful in a person's life. At FIU and within our college, we're deeply committed to preparing the next generation of biomedical engineers. Our commitment extends beyond providing an outstanding education, which I'm confident you're getting. We strive to cultivate innovation, encourage interdisciplinary collaboration, promote ethical leadership, and foster partnerships with healthcare providers, industry, and the broader community. We want you to leave FIU with these exceptional technical skills and the creativity, compassion, and entrepreneurial mindset needed to solve our most pressing problems. Today's presentations are an opportunity to showcase your technical accomplishments and improve your ability to communicate ideas, defend your work, and collaborate with others. Those are critical skills that should carry you throughout your career. I encourage you to take pride in what you've accomplished, share your work with confidence, learn from the questions and feedback you receive, and celebrate how far you've come. Today's presentation extends beyond a project conclusion. It's another important step in what I hope will be a rewarding career for you. I want to thank sincerely our faculty, our mentors, our industry partners for their inspiration, their dedication, their guidance, and their patience in working with you. Your mentorship plays a critical role in shaping the future of our biomedical engineering students. And to the students today, I wish you the best of luck. May your presentations reflect your hard work, your curiosity, and your dedication that brought you here. More importantly, I wish you continued success as you embark on your careers that will improve your lives, strengthen communities, and help shape the future of healthcare. Thank you. Have a great day.
Thank you.
Thank you.
Senior Design Expo and Competition is really the culmination of a year-long study. We're in the first semester under the direction of Professor Sharstani. He's over there. Let's give it up. Students are taught the rudiments of medical device product design, development, and manufacturing. They also attend workshops in the use of state-of-the-art software tools such as SolidWorks and ANSYS. In addition, students form teams and engage the biomedical engineering community to secure projects. And many of these projects are locally, but also nationally and even internationally. And they work with these companies to identify and secure sponsorships for the projects that address unmet biomedical needs. First semester ends with students presenting their project proposal before a panel of biomedical engineering faculty who engage their technical decision-making, challenge their decision-making, and evaluate the scope and feasibility of each project. Upon approval, students are assigned to a faculty mentor who provides supervision throughout. They're also assigned to an alumni mentor to assist them along the way. The second semester, meaning this semester, students work to finalize their designs, manufacture working prototypes, attend weekly lectures, focus on product development, and also there are lectures that address career development. Today I'm pleased to announce that the senior design program is healthy and continues to grow in all areas. The number of projects has actually increased. This past academic year, ending today, there are 23 projects this year alone. That's up from 20 last year. We've shown great increases in financial sponsorship per project. It's actually holding steady. It's about $1,500 on average per project. The number of first-time sponsors is also ticking up, as well as the number of repeat sponsorship. Of course, none of this would be possible without the hard work of our students and the generosity and vision of our sponsors and the guidance of their faculty mentors. Let's give them all a round of applause. I say we just get right into the competition. Why wait? Yeah? Okay. So now for the competition. Okay? But I'd like to first introduce the judges. And right on time, Ms. Brianna Woods. Timing could not have been better. Let's give it up, Ms. Brianna Woods. The Global Product Data Security Manager at Stryker. To her left and my right is Mr. William Williamson. Let's give it up for William. Working here at Cordis, a veteran of sorts. And to Brianna's right and my left is Mr. Anthony Higgins, and he's a senior product development and manufacturing engineer at Engineering Resources Group. Let's give it up for Anthony. And
wrong, by the way.
I'm not looking at that. No, I never pay attention to that. And of course, Ms. Maria Montoya. I haven't seen her in a while. She's been working in the field. She's also at Stryker.
I'm at Stryker, yeah.
At Stryker.
For advanced operations.
And for advanced operations. Let's give it up for. I'd like to take care of a little bit of housekeeping before we move on. Right in front of the room is a table, and you can see these booklets. Yes? You open your booklets. Some booklets down front. Yes? You will see the agenda for today. Teams will go in order of numbers, and we'll break for lunch at noon. At that time, the judging panel will retreat to EC 2608. I think that's it, the DME conference room for their deliberations. Lunch will be at the Panther Pit for everybody, and at 1 p.m. we'll start the poster competition. Yes? After the poster competition, we convene back here at 2:45 p.m. for the awards ceremony. So please govern yourselves accordingly. If you are here for the first time in the engineering building, the facilities are just right across the hall. Yes? So let's get to the competition, the rules. Each team has 10 to 12 minutes to present their project. At the 11th minute, the bell will toll once. Tells you that you have another 1 minute to go. At the 12th minute, you will hear tells you that you have 30 seconds to finish. Yes? And so I'm sure that's means of practice and they're within the rules of the competition. As far as awards later on, what to expect, first, second, third place for oral, first, second, third place for poster competition, also honorable mention. Of course, best presentation and also outstanding project manager. So I say let's jump right into it. Let's call team one to the stage. Team one. NOVA, Novel Versatile Adaptive Cervical Spacer System. The faculty mentor is Professor Dargam, sorry. Alumni mentors, Ms. Chelsea Jai Prasad and Melanie Villamar Molina. The sponsor of the project is Cutting Edge Spine. And the team members, led by the manager, Catherine Alexander, and Gabriel Calero and Michael Cabral. Let's give it up for team number one.
Hello, hello. Good morning, everyone. We're Team 1. My name is Gabriel. I'm joined by Catherine and Michael, and today we're going to be presenting our Novel, Versatile, and Adaptive Cervical Spacer System, or NOVA, sponsored by Cutting Edge Spine. Your discs are degenerating as we speak. This is the process where, over time, due to both compressive and frictional forces, your discs start to break down and can even start leaking fluid into your spine. This, over time, can lead to severe pain and mobility issues. And while people tend to start with more conservative measures such as physiotherapy to try to deal with the symptoms, the actual root of the issue needs to be taken care of through more intensive measures such as ACDF, which stands for Anterior Cervical Discectomy and Fusion. This is a procedure where, as you can see, your disc needs to be removed and replaced with a vertebral spacer to maintain that height. And that spacer is then fixed in place using either a plate and cage method like the one you can see here, or integrated screws like in the standalone approach, which we'll get more into later. However, for now, I'm going to pass it off to Catherine to get deeper into our actual clinical needs.
Thank you, Gabriel. From a global awareness standpoint, each year over 130,000 patients undergo ACDF procedures in the United States alone. Despite how common this procedure is, current solutions do not allow surgeons to adapt fixation intraoperatively based on their patient's anatomy, bone quality, or overall stability needs. This lack of flexibility becomes increasingly consequential over time, as up to 25% of these patients will develop adjacent segment disease within 10 years and require secondary surgical intervention. In these cases, surgeons often have to choose between limited fixation or a much more invasive procedure that involves the removal of hardware. There's also a significant business opportunity. The spinal fusion market was valued at over $2 billion in 2024 and is predicted to surpass $7 billion by 2034. NOVA will uniquely appeal to both standalone and plate-preferring surgeons and introduces value by avoiding hardware removal in revision procedures, reducing inventory burden, and allowing surgeons to bill separately for instrumentation, all of which give us a competitive advantage on the market. Let's take a look at those systems. So, right now, the current market is split between two systems. Surgeons can either opt for the standalone option or a more traditional cage and anterior plate construct. Standalone systems are fixed with just two integrated bone screws. That lack of anterior hardware preserves adjacent level access, but these systems don't offer the high stability that's often needed in more complex cases. In those cases, surgeons need to use the cage and plate construct, which is very stable, but at the cost of a much higher anterior profile. That large anterior plate covers a large portion of the vertebral body, and so that's that hardware that typically needs to be removed in the revision procedures that we talked about. Our challenge was clear. We needed to deliver an adaptable cervical spacer system that's compatible with revision procedures and offers optional supplemental fixation where needed within the allotted timeline and budget. To meet these goals, we proposed NOVA, one system that combines those previously separate approaches into one adaptable platform. This ties in global engagement, one spacer, 3 configurations, standalone, cage and plate, and a third novel hybrid option. This, along with the fact that the plate can be attached in situ after cage placement, gives surgeons the ability to adapt fixation based on their patient's needs and the unique versatility to change approaches during surgery without needing to switch to an entirely different platform. For a patient, this means a solution tailored to their case, and for surgeons, this means far greater control. We'd like to highlight some of the requirements that most directly impact NOVA's value. Most critically, our device must provide sufficient immediate mechanical stability, which was benchmarked against established performance targets from the literature. To be a true hybrid, one spacer needed to be compatible with at least both standalone and plated configurations. To be competitive with the current low-profile systems on the market, our supplemental plate needed to be less than 2 millimeters in thickness, and its footprint needed to preserve access to adjacent vertebral levels so that future instrumentation could be placed alongside existing hardware rather than requiring its removal. Our cage was designed with a porous lattice to promote osseointegration and bone fusion. Here's some additional material and dimensional requirements. Now Gabriel will walk us through how we translated these into a design.
Thank you, Catherine. So, in our early design phase, we had 3 concepts that we were originally exploring. The first being what we thought was our most obvious and intuitive approach, a central fixation approach. Here, essentially what we did was we added a central threaded hole where we could put a screw and affix the plate onto the cage itself, allowing for that versatility that we were talking about. However, due to the limited amount of space on the face of the cage itself, it presented us with some possible structural issues that we didn't feel comfortable moving forward with. That's why we moved on to our second approach, our hybrid fixation approach, which has 1 threaded plate screw hole and 1 integrated bone screw hole, still allowing for that hybrid fixation that surgeons were looking for. However, since we only had 1 of each hole, it significantly reduced our configuration flexibility and didn't allow for the adaptability that we wanted intraoperatively. So we decided that we needed to marry the best of both approaches, and we came up with our dual hole approach, which hosts a nested fixation pathway, actually having the threaded plate screw hole embedded inside of the integrated bone screw hole, allowing the surgeon to choose which fixation pathway they want to move forward with, allowing for an overall more compact and versatile design. Our cage went through several changes during the design process. However, the most important of these being the addition of that second nested fixation pathway. Originally, we only had the one to try to preserve some of that porous structure in the middle of our cage, but after meeting with our surgeon advisor, he told us that the trade-off of having the extra adaptability was worth losing some of that porosity. Our cage has 3 main key features. The first one being that anti-rotation lock here on the left, which is designed in order to lock the plate onto the surface of the cage itself and prevent it from moving around during installation, allowing it to be easier for surgeons to actually use. That middle there is showing our interior porous lattice region, which serves 2 main purposes. Number 1, it helps promote osseointegration, and number 2, it helps lower the elastic modulus of our cage to better match that of bone and prevent any unnecessary subsidence. And there on the end, we're showing our anti-expulsion teeth, which we designed to be at least 1 millimeter in depth to get good purchase on the bone and prevent any migration both during installation and fusion. Our system has 2 main types of screws. The first being our plate screw, which has an anti-crossthread feature on the end, making it easier for surgeons to actually install. And the second being our self-tapping bone screw. Both of these have a T10 hexalobe head, as is required for our ISO 10664 standard, allowing them to be used in any OR in the United States. The main novelty with our proprietary plate configuration is that it preserves 50% or more of the anterior face of the vertebral body, allowing us to do multi-level surgeries without ever needing to remove any of the existing hardware. And as you can see, we designed them in a way that they are not only compatible with each other, but with any of the plates that are currently on the market, allowing surgeons to use our technology for initial surgeries and any revision surgeries, regardless of the hardware that was originally used. This is not something that is currently on the market, and is a huge breakthrough for patients that have adjacent segment disease, because it saves them the trouble of having to recover from an extra procedure, especially in that older age. As we mentioned before, our cage is compatible with 3 different configurations. Now let's get into how these actually come together. The first being our traditional standalone approach, which has 2 integrated bone screws, one going into the superior and one going into the inferior vertebrae. The second is our 2-hole plate option, having a plate screw affixing the plate to the cage itself, and 2 bone screws going through that plate, both again into the superior and inferior vertebrae. And finally, our most novel approach, the hybrid approach, which has 1 integrated bone screw going through the cage, 1 plate screw fixing the 1-hole plate to the cage, and then another bone screw going through the plate, either into the superior or inferior vertebrae, depending on what is necessary for that surgery. Now, as you can see, our prototype is very small, and because of this, we put a lot of emphasis on our FEA so that we could properly analyze our system. The 2 main simulations that we had to run were our compression and compression shear tests. And as you can see here, we passed both with very minimal deformation. Also important were the simulations that we had to run on our plates, both our static compression and fatigue loading. And as you can see here again, we passed with very minimal deformation and very minimal damage overall. Michael's now going to walk us through our manufacturing.
Thank you, Gabriel. Alongside FEA, we also use 3D printing to show us if any changes needed to be made before we produce our final prototype. After fixing these errors, we're confident enough to actually produce it. It is fully made of medical grade titanium, and we use additive manufacturing through laser bed powder fusion to create it. It has a resolution of 0.25 millimeters, which allows us to preserve the complex porous lattice as well as fixation features. Keep in mind, our device was fully 3D printed, but in the future, only the cage will be 3D printed and the rest will be parts will be machined. Once we have the cage, we have into our testing. Our main test is our killer test, which we use for our mechanical stability, and we divide it into 3 separate tests. All of our values are from literature and use a factor of safety of 5 compared to physiological loads. Our first test is our static axial compression test. To do this, we use a universal testing machine and applied 6,000 newtons of force to the cage itself. During this, the cage remained within its elastic region and there was no long-lasting deformation. This means we passed our acceptance criteria. Similarly, our compression shear test also remained within the elastic region and passed. The only difference is the setup itself. We used a fixture to keep it at 45 degrees and applied a force of 3,000 newtons instead. Finally, our last test was our screw pull-out resistance test. To do this, we used a scale and our weight on the other end to apply 500 newtons of force to the screw itself, and during this, the screw was not pulled out nor damaged, once again passing. In total, we had 13 verification tests, including dimensional measurements, document analysis, and mechanical tests. Here are our main ones that distinguish our device from other devices on the market: our increased fixation features, our low profile, and our porous element. All 13 of our tests passed and remained within our desired tolerances, meaning we met our expectations and requirements. We had a budget of $500 and we remained below it with a total cost of $483. Our unit cost is calculated at $110. Our device is a Class 2 medical device and we must follow FDA 510K clearance, meaning we must show substantial equivalence with other devices on the market. Instead of just using one predicate device though, we use a paper that compiled many. To follow our regulatory pathway as well as validate our factor of safety, we use these ASTM and ISO standards, the main ones being mechanical stability, subsidence resistance, and bone screw pull-out respectively. Looking forward, we must perform official ASTM testing so that we can move on to cadaver evaluation and then in vivo analysis of our porous elements and see how it promotes bone fusion. Ultimately, from a global perspective, we have combined the advantages of the other spaces on the market, as well as added our own features to create a novel, versatile, adaptable solution that surgeons can use to give patients around the world treatment tailored to their specific needs. This expands opportunities not only for the hospitals and the surgeons, but for the actual people affected by degenerative disc disease. We'd like to thank everyone who helped us throughout this project and the BME department. And as Gabriel said, your discs are degenerating, and if you need surgery, this is the flexible solution you're going to want to use. We thank you again, and we open the floor to questions.
Okay, you can hear me? I think first I want to say great job. You could tell that you guys worked really hard on this, and I can see it in the presentation. You guys have a very much a DFM, like a design for manufacturability mindset, and I can see that. So maybe one question I had was, did you guys see any issues with machining tolerances with such a small device? So like how did that affect your prototype?
Thank you for that question. So yes, it was kind of difficult for us to find a manufacturer that would go down to such a small resolution because our board structure was designed very specifically to maintain a range of post sizes. And so that resolution was very important and would drive up the cost. So it took a while to find the right manufacturer for us, but we started looking very early to make sure it wouldn't delay us.
Awesome. And did you have to change any of those tolerances after you started machining it, or?
No, so we did do a lot of thorough research beforehand to kind of get a range of what we would be able to do going into it.
Thank you.
Great job.
Thank you.
You all do a really good job at speaking, so that's also a plus. My question is on the screw testing. In the picture, you only showed, I believe, this design. Did all three adaptability design pass the screw test?
So yeah, so the screw pull-out test was just, the only reason that we have that plate on there is so that we would have something to actually grab onto the screw with. Because it's so small, it was difficult for us to get a good purchase on it to pull it out. So that test was just us making sure that it wouldn't pull out of the bone itself. So we didn't need to test all three configurations with it, it was just making sure that our threads were big enough to actually grab onto that cancellous bone.
Okay, did any of your surgeon advisors have any concerns about the different screw adaptabilities?
Not necessarily. They were actually more excited more than anything else because they got more adaptability, they had more options. So.
I now call Team 2 to the stage. Gyrofuse, anterior lumbar interbody fusion cage for reduced vertebral subsidence. The faculty mentor is Dr. Andrew Lee, alumni mentor Ms. Sharik Vega, and the project sponsor is Atlas Spine. Team members, Emily Duenas, project manager, Pablo Boada, Kevin Del Valle, and Julian Castillo. Yep, let's give it up for the team.
Good morning, everyone. My name is Kevin. This is Emily, Julian, and Pablo, and we're Team 2 for Senior Center 2026. Our project is Gyrofuse, a multi-material anterior lumbar interbody fusion cage design for reduced vertebral subsidence. And our sponsor is Atlas Spine. To treat lumbar conditions, an anterior lumbar interbody fusion surgery is performed, better known as a native surgery. In these surgeries, the disc is removed from the anterior side of the patient, and a weight-bearing spacer is put in between to maintain the disc height. Now, these surgeries are done mainly on patients who have degenerative disc disease, as well as spinal stenosis, where the top vertebrae starts impinging on the nerve roots, causing debilitating pain down the back and legs of the patients. For that reason, cages have multiple objectives they need to follow, such as maintain structural stability, maintain disc height, load distribution, as well as promote osseointegration of the top and bottom vertebrae. Unfortunately, in the current market, there are multiple cages that fail in some type of way. For example, solid titanium cages have high stiffness, while PEEK cages have bad osseointegration. The titanium cages cause stress shielding over time, which leads to weakening the vertebrae, while the low bowel inert of the PEEK leads to low osseointegration in the early stages of post-op surgery, leading to subsidence, the implant sinking into the vertebral bone, causing debilitating pain in the patient's spine. For that reason, we spoke with surgeons to make sure that we had the right scope, and they agreed. Osseointegration as well as mechanical stability is an important factor to take into consideration for native cages. Now, our objective is to deliver a multi-material prototype which focuses on promoting osseointegration while also lowering the stiffness at the vertebral end plates to reduce the risk of subsidence for the patients. Now, our target demographic were patients that were 35 to 50-year-olds. We picked them for two main reasons. They have the least chance of being osteoporotic while also having the highest ALIF cage surgery rates, leading to a good basis for design inputs. Now, aside from the clinical need, there's also a huge business benefit. The current ALIF market is valued at around $11 billion and is still growing to this day. Now, revision surgeries occur in up to 23% of patients due to subsidence, and these can cost between $40,000 to $80,000, which Gyrofuse brings a good value to the market by saving money and time for both patients, surgeons, and insurers. Now I'll pass it on to Pablo, who will talk about our current modalities.
Thank you, Kevin. So before starting our design, we actually did some research on the current designs that are available nowadays, and the most common materials used for this kind of applications is PIC and titanium cages. So the good thing about PIC is that it is close, or it has mechanical properties closer to bone. And the negative part of that, though, is that PIC doesn't have a good osseointegration. So it's not good for bone ingrowth. And which is important for integrated fusion cages. So titanium provides structural strength, it promotes osseointegration, but it's too stiff, which can increase the chances of subsidence. So now that's when Gyrofuse comes into the picture. So by combining a porous titanium cage core, providing structural strength and osseointegration, and also a sleeve, that instead of being big, it's actually non-hydroxyapatite, which is a composite that is, it also has mechanical properties closer to bone, but is bioactive, which promote osseointegration. So this is just our main designs, pretty much guided, med requirements that guided our main design, which just wanted to have an implant that it was capable of withstanding spinal loading conditions. It was able to distribute load efficiently. It was able to fit within the disc area and reduce localized stress on the end plate, and also be biocompatible, and be able to sterilize with ETO. So the main takeaway of this slide is that there is no one single material that actually provides all that we need. So for that reason, by combining non-hydroxyapatite sleeve and also a porous titanium core, we can get this great balance of strength, osseointegration, and reduce stiffness, which can improve patient outcome. So this is something interesting. We tried different lattices, and at the end, we found out that gyro structures are actually better and low distribution. And we think it's because of this continuous structure that with no sharp corners that actually helps to distribute better these loads. And we figured out, so we came up with a lot of designs throughout this whole project, and we just focused on actually design for improving manufacturing, which was the main issue with design concept 1, osseointegration and locking mechanism, which was the main issue with design concept 2, and then some fitting and finishing designs, that was the main issue for design concept 3. And then that's how we finally got to our MVP, which it was the one who best met our requirements, and the one that we took for the next phase for simulation and testing, that now Emily's going to talk more in depth about.
Thank you, Paulo. Now, to assess the mechanical behavior of our implant, we conducted finite element analysis using ANSYS. This is one of our primary simulations, which we analyzed the implant with the vertebrae under physiological loading. And these are the results, which shows uniform load distribution and minimal stress concentrations at the vertebral end plates, demonstrating its stable mechanical performance. We also analyzed the implant during standing conditions, as well as during flexion, which in both cases it showed minimal deformation, which proves its structural stability. Now, having these successful verification results, we got into our manufacturing phase, which for our titanium core, we used selective laser melting using an outside company. And then for our NHA PA66 sleeve, we explored in-house fabrication processes such as casting and sintering. This NHA PA66 final sleeve design requires the necessary specific material parameters in order to consolidate this material in solid form, which was outside of our project scope. Therefore, we decided to use carbon fiber reinforced PLA as our surrogate material, as this material provides the similar combination of stiffness and mechanical behavior necessary. Now, we use electron scanning to compare our titanium core with a commercially available titanium implant. And this is one of our key advantages of our design. As you can see, it has open interconnected pores, which allows for osseointegration, whereas this commercial implant, you can see that it has a dense surface with less interconnected pores, which limits bone growth. Now, we considered the practical implementation of our design in the OR. The titanium core and the composite sleeve will be provided as two separate sterile components, which the surgeon will insert the core into the sleeve, interlocking thanks to our simple locking mechanism. Then the surgeon will apply the bone graft placement before implantation. Now, for our verification, we did compression testing to verify our elastic modulus and our displacement. Our implant had an elastic modulus of 0.5 GPa, and it also experienced a 0.6 millimeter displacement, which is below our design limit of 0.7 millimeters. We also did dimensional verification using a caliper to verify all our critical dimensional components. We also did compression testing with the vertebrae foam blocks to analyze maximum concentrated stress, which we got a 4.9 MPa, which is way below our design limit of 6 MPa. Also, for our verification requirements such as core porosity, weight, biocompatibility, and ETO sterilization, we all met our design requirements. So overall, all of our 8 design verification met our required design criteria. And now we'll pass it on to Julian, who will discuss our cost analysis.
Thank you, Emily. So an important part of verification testing is its cost. For our cost breakdown, our implant costs $1,112 to manufacture, which shows that it is economically feasible, and this is all done within our budget. So when looking at regulatory pathway, our device lands as an FDA Class 2 medical device, which must adhere to general controls for strict device labeling and special controls for specific mechanical testing parameters. On top of this, we must conduct a 510K notification to find subsequent equivalency of predicate devices in the market. And on top of this, if there is none, we must pursue a PMA pathway. So when looking at engineering standards, we considered biocompatibility, subsidence testing, compressive strength testing, and 21 CFR to match the regulations of what is needed by the FDA for commercialization of the device. So when looking at intellectual property, we looked at many patents currently in the market, ranging from gyroidal lattices to porous surface on the implant, and many others. And the patent opportunities for gyrofuse are high since there's no current active patents that goes against our proprietary design. So when looking at a summary of our accomplishments, we were able to design and manufacture a gyroidal lattice core mixed with the combination of the nanohydroxypolyamide 66 sleeve, and there is no current combination in the US market right now. And we were also able to acquire the polyamide 66 with nanohydroxyapatite for the US market, since it is currently only used in Asian markets right now. So when looking at the future of gyrofuse, we would like to do further verification testing such as cyclic fatigue testing and do in vivo testing to see how much osseointegration has occurred in the implant after months of implantation. Additionally, we would like to make patient-specific cages, such as changing the lordotic angle and doing osteoporotic versions of our cage. And on top of this, we would like to focus on surgeons to change their screw hole angles to facilitate their ease of use when doing surgery. I'd like to take this time to acknowledge the FIU BME department and our sponsor, Patrick Kennedy, for their guidance to our project. Ladies and gentlemen, Gyrofuse. Stability by design, fusion for life. Thank you.
Thank you, Gyrofuse. Great job, you guys presented very well. One great thing I noticed is you guys explained the market need really well, so it made the problem really easy to understand from something like me. A question I have, I know you mentioned the material was out of scope of the project because it was difficult to source. So what would be the alternative plan if, let's say, mass production, you could not source the material? Not sure if it's concise enough, but.
Thank you very much. So basically, nanohydroxyapatite polyamide substitutes. It is a material that's been used in the Asian or Turkish market, and there has been research papers on their manufacturing processes. We tried to do it at home by censoring it with our own mold, and we were able to turn it into a solid, but we weren't able to fully manufacture it. Now, if companies are a little more comfortable with the material, they can experiment using hot press compression molding, as well as laser bed product. I'm not sure if that's the exact one, but most companies that we contacted, due to our time constraints and also the exotic material that they're not used to, they rejected it. But in the future, as more research is done, maybe they feel more comfortable to manufacture just as regular powder material.
And I have probably one more question. I saw I think it was the fatigue testing. So how does the durability of the proposed material product compared to what's in the market? How are the other products performing for durability and fatigue?
So, for example, the titanium cage is amazing when it comes to fatigue testing, but it has stretch filling. So we have the sleeve, which still conforms after the fatigue testing over time, but it's still a composite material. So it will conform, but it will withstand those forces over time with the support of the titanium cages. And actually, there are single material nanohydroxyapatite cages that were experimented in the Asian market, but they have that problem where they're not good at load distribution after they conform enough. So that's why we decided to use a titanium core that doesn't touch the vertebrae to allow for load distribution and support for our sleeve.
Thank you.
Was there any findings during your evaluation that when you compared to a standard baseline, you had a failure and you had to go back and redesign or change your material? If so, what was it? Everything performance expected?
Thank you for the question. Actually, more like an actual design that we manufacture, it was more in simulations. So one of the concepts that we have in this concept too, it has this overhang and the locking mechanism, and we through simulations we identified that it was a super weak spot, and that's what's going to play. And then we had to redesign upon that to try to reduce costs afterwards. So does that answer your question?
Yes.
Great job, everybody. My question came to the manufacturing cost. I think you guys said it was between $1,000 and $1,500. That was only the titanium piece, or that's projected to include the sleeve?
That's with the sleeve.
With the sleeve? Okay.
Yeah, it's with the sleeve.
What's the comparative cost to competitors for their manufacturing costs? Did you guys look into that?
I mean, it's kind of difficult to range since our material isn't really used here in the US, so that's a big void in our analysis in that case.
Okay. And then, I might have missed it, are there other comparative products that have a sleeve that function properly?
Yes, but they're made out of PEEK.
Okay,
So-
the PEEK, sleeve is the PEEK.
Yeah, so
Okay.
it's titanium core and then the PEEK sleeve on the outside.
Okay, thank you.
Okay, thank you, team number 2. I now call team number 3, oh, they're already here, to the stage. SMART, negative pressure wound therapy. Faculty mentor, Dr. Shuleng Zhao. Alumni mentor, Ms. Naya Martin. And the project is sponsored by JCAT Biomedical. The team is led by Ms. Magda Escobar. Other team members, Andrew Izalahoy, Bruno Quiterio, I hope I didn't ruin your name, and Roberto Herrera. Let's give it up one more time for team number 3.
Okay, good morning. We are Team 3, and this is the Smart Negative Pressure Wound Therapy device. So we wanted to start off with what are diabetic foot ulcers. Diabetic foot ulcers are non-healing wounds that come about from patients that have diabetes that don't really feel that the cut or the wound is forming because they have neuropathy, as well as poor circulation. So that wound starts forming, they don't feel it, they don't see it, and it becomes a non-healing wound. This is where negative pressure wound therapy comes into play. You put on the negative pressure wound therapy device with that cover, and it sucks out the exudate, the wound fluid, to make sure that that non-self-healing wound is able to heal. Currently, the problem with these devices is that the changes are from about 2 to 3 days. So the doctor puts on the bandage, the patch, and then about 2 to 3 days afterwards, that's when they take it off, and there's no real monitoring that occurs within this period. So sometimes infection can set into these wounds, and that's what we want to avoid, is the patient getting this wound infected. That puts our patients at risk. Why? Because afterwards they have hospitalization and they have to deal with possible amputation. About 12% of Americans in their lifetime will develop diabetic foot ulcers. 30 to 40% of these people will have a 5-year mortality rate thereafter. So it's not ideal to have infection setting in between those wound dressing changes. Current modalities for the NPWT or for diabetic foot ulcers are either patches, dressing changes, without any exudate removal, the NPWT device that has the exudate removal without the monitoring, or the monitoring devices that tell you whether the wound is getting better or not, but it doesn't provide that negative suction. Our device seeks to do both. Provide the negative therapy suction as well as the monitoring. So between those dressing changes, we can see if infection is setting in or not. Now we have Bruna with our project scope.
So first, I'd like to explain a little bit our project scope. So we designed a proof of concept, smart NPWT device, rather than a clinical ready device. So we combined both the negative pressure therapy with continuous monitoring through pressure, color, and temperature sensors. And so this demonstrates that it is possible to have both the therapy and the continuous monitoring in one single device. Once we define our project scope, we need to translate those into measurable engineering requirements. So our system maintains a pressure of -80 to -125 milliliters of mercury, while always continuous monitoring the color of the exudate, the pressure, and the temperature of the wound. So we chose those parameters because they show us great value of the wound state, such as worsening or any kinds of infections. Besides the clinical requirements, we also need to think of the prototype as a practical thing. So that's why that means building a lightweight portable device with the continuous monitoring sensors, a fluid pathway that's sealed so it's not so prevent leaks, and also a material that will eventually meet the biocompatibility requirements. And since our goal is to one day this become a real product, we also need to follow some of the regulatory assessments. So according to the FDA classifications, our medical device will be classified as a class 2 medical device with a 510K regulatory pathway. And also, since we added some sensing capabilities, we would also be required to do additional validation. And in addition to the regulatory assessments, we also need to follow some engineering standards. These standards, they cover things such as risk management, electrical safety, quality management, and also biocompatibility. And while our prototype is only for benchtop testing, we follow these standards, so we'll help the future improvement of our project. And so finally, I'll briefly explain how we actually build a prototype. Oh, I'm so sorry. So first we use SolidWorks to design the enclosures and the components of the mechanics. And we 3D printed, and this made us capable of rapidly prototyping, testing, and also redefining the design of our project, while also integrating the pump, the sensors, the canister, and the tubing, and also reducing the time and cost of the project. And now Andrew with the sensors.
We already understood the capabilities of the device, but how does it actually happen? Well, liquid has a natural tendency to move from the higher pressure region to a lower pressure region. So the answer was to induce a vacuum system or induce a vacuum regime. That could be achieved through a mini diaphragm pump. And in that way, we induce this bias to the progression of the liquid so that the exudate can be extracted from the wound bed. Also, this is just the show of the dressing that is collecting the peri-wound temperature and the peri-wound oxygenation through oxygen and temperature sensors. In this case, it's the oxygen sensor. The oxygen sensor was added after the design part because at the beginning the sponsor wanted to have a perfusion-aware system, but because of the scope and the timeline of the project, it couldn't be included. But because we finished early our goals, we were able to add and keep adding value to the sponsors. In this case, that's how it would work. It essentially what it does is just targeting the dynamics of oxygenating the oxygenated hemoglobin and through the dependency of the wavelength for absorption. In this case, this is the RGB sensor. The RGB sensor is crucial because it is capturing the data from the color of the wound exudate. The exudate color is fundamental because it tells to the physician if the wound is progressing or is worsening. In this case, also the temperature sensor. The temperature sensor is an RTD, it's ideally, but the way that we did it was just with the thermistor, but basically it's the same principle. You have a material whose resistance is dependent on the state that it is. As heat enters the system, the state would evolve. It might first increase the entropy, and in the same way would increase or change the anisotropic pathway that the current would follow, and therefore alter and affect the resistivity of the resistance of the material. In this case, this is the ultrasonic sensor. Because we weren't able, because of the budget constraint, we weren't able to add a microflow sensor. We said, oh, but we are capturing data constantly with time, it's logging it. And what is flow but actually volume per time, right? We just included then the volume capture. How did we actually calculate the volume? Well, it's easy. The geometry of the canister is fixed. We could just adapt that geometry to alter the variable that would be the height. The height changes with the ultrasonic sensor. As it sends the signal, the time delay that it takes to get back, you can infer the distance that we are using. And with that distance, we then just calculate the volume, and we can calculate the volume like real time. Volume exudate production is also a key parameter for the physician to assess if the wound is progressing or worsening. In this case, this is the circuit schematics. The circuit schematics, as you can see, this will be the microcontroller. This was separated for the purpose of illustration, so it can be easier to identify the logic. This will be the thermistor. The buzzer is just for error modes in the system, so the patient is also aware, because the system does have a telemetry module. In the future, it should be connected to the physician, and the physician should be receiving real-life updates. So you can be, the problem that we were having is what Sophia said, that between wound changes, there is evolution of the wound state that might be critical and that might be caught on time. So this would improve physician intervention and therefore better patient outcomes. In this case, this is the simulation. In this case, we didn't do an actual simulation before building the prototype. What we did was just the control logic simulation. We assumed that if we had a system that was able to actually collect the meaningful data we were trying to get, meaning pressure information that could be achieved with a pressure sensor. If we could input that data, that's the control system works, meaning if the pressure reaches a certain value, do we have a way to modulate the pressure back? In this case, yeah, we would use PMW to modulate the pump, but they don't follow linear dynamics. So that took a lot of trial and error to get the pumping to work the way we wanted. And this is just the integrated of all the sensors at the same time working, as well as the all RGB optical responses of each of the 5 wound isolated states that we try to analyze. In this case, this is a cost analysis of the project was below $1,000. That was our general budget for $910. In this budget is also included the part of the marketing because we have a website just for outreach. So the actual cost per component is a little bit low. Now we move forward to how this process began. Well, this is our first design concept. And with the design concept, this is a decision matrix. The decision matrix has its own logic for the purpose of simplification. We just showing the values, but essentially what we did is just did technology feasibility, did the market requirements, and then did the sponsor value. So of all these market requirements, what would be the most valuable for the sponsor? And so then we multiplied all those values and did like a linear combination normalized to like weighting coefficients for each of the 5 market requirements. Then Roberto will cover it.
Thank you, Andrew. For our second design concept, as you can see, it actually performed better across like all of our metrics, but due to feasibility constraints like time and budget, realistically speaking, we couldn't achieve what we were set out to do, simply because putting all of the sensors as well as the pump and integrated within the wound interface just would make the device to have to be lighter and, well, within the time that we had, we couldn't do that. As far as our second design concept, third design concept, which is also our MVP, we decided to integrate the temperature sensor at the wound interface and integrate the color and pressure as well as volumetric sensor within the controller, as well as putting the canister below the controller for it. As I said, this ended up being our MVP. It ended up matching all of the requirements that we set out to achieve. For our first verification test, we first tested how the system would react to a leak within the system. We identified that the system was able to not only detect when a leak happens, but once the leak was resolved, it would return to our expected metrics. For our third verification test, we tried an occlusion test with higher viscosity fluids. We noticed that the pressure kept, since it was a partial occlusion, the pressure maintained parallel, but the flow decreased. Once that blockage was resolved, the flow returned to regular operation. So it passed the test. For pressure regulations, we just tested it 5 times, running it for 2 hours to see if the device was capable of maintaining the set pressure during that entire time. As far as our temperature testing, we tested our temperature sensor versus calibrated thermometer to test whether the measurements obtaining from the sensor matched the thermometers. And now Fiorella with color testing.
We were able to verify the RGB sensor by testing different color liquids to simulate the exodus of conditions. So the sensor was able to measure red, green, and blue intensity, and it was able to also separate them. So we were also able to evaluate the measurement capabilities by using the coefficient of variation, and the results show that the sensor does provide different repeatability readings. For global awareness, millions of people in the world suffer from diabetic foot ulcers, and the late testing causes infection and even amputation. We will aim to fix that with our device. So for a device like this to work, it should be affordable, portable, and easily accessible for the public. For our global engagement, we use mechanical, electrical, software, and biomedical engineering to build and test a functioning benchtop prototype. For our future work, we would like to miniaturize our device, also possibly add more sensors and improve user interface. We would like to thank our sponsor, the BME department, and everybody else who helped us throughout this journey. Thank you very much. Are there any questions?
Thank you, team. I thought that was a great project, and I like that this is almost on the borderline of preventative, you know, versus just reactive medicine. So I did like that. So what would be the plans for like false alarms on, you know, sensors? So in detecting that there could be an infection, maybe there's not. What would be kind of the next step for dealing with false alarms, and next steps for the healthcare provider and the patient?
We will have a time dependency. In this case, you just see how long the same signals are maintained, and if they are maintained for a certain period, given, well, first you need to, once you finish the system, measure the whole certain or whole the specificity of the system, how well it can identify the wound state. Based on that, then you will match it, how the readings are just drifting away from that confidence level. And with that, you could just add an extra parameter where the uncertainty increase, so you just would need physician intervention. You just say, hey, this reading needs attention. You just bring the physician into the logic of the device. Actually, one of the capabilities of the device is that you can customize the thresholding and the temperature study.
Okay, thank you. So what's the normal expected time, based off your research, that a patient would need to wear the device?
It all depends, because even if the patient has the device, not all wounds progress equally. So in an average, it would be for the therapy with the device, it would be for non-severe wounds, that it's the main focus of the device, would be like 5 to 15 days normally. But like I said, one of the points of this is just that those type of infections bring complication and prolong the stay at the hospital. So in average, I would say from 5 to 15.
Okay, so this is worn in the hospital and not with the patient at home?
But no, that's one of the main
So our device, that model that you see there, is what essentially they would be wearing, and it's meant for it to be wearable at home. That's why we have included that when it does beep and make those noises, it needs to be checked. The person has the ability to say, hey, I need to go to the physician and understand what's going on under my wound. Normal negative pressure wound therapy devices, they're usually hospital bound, which means the patient has to be laying down there in the hospital for 2 weeks. They have to pay a ton of money, insurance. I know you guys all have probably dealt with insurance and medical devices. With this device specifically, the person can be walking around and wearing it. It's similar to the Pico device. I don't know if you guys have ever come across the Pico device, except this one has sensors put into it. So the person can be at Costco and they can be like, oh my God, I'm getting infected. Let me see if I can schedule a doctor to see what's going on, see if maybe I need intervention.
Okay, so I was leading to my next question, was about battery life. Is that a part of the consideration of your device? If they're wearing it at home, how does that go into the device and the design?
Yeah, one of the market the design inputs was the battery life. The battery life, it should reach about 18 hours continuously operating before it needs recharging, because the most probably the time the patient will actively wear it, it's at around like 16 hours in the sense that you cannot continuously apply the same type of pressure, so the device can be disconnected while still having the wound dressing. So in one of the pictures there in the ceiling of the dressing, there is like a cap, and that's one of the main purposes of the cap. Because as it is progressing, you might not need to have the therapy anymore, but you might still benefit from monitoring continuously. And because the sensors are embedded in the dressing, you still get the benefits of the device. Modularity was one of also the main points.
Okay. All right. In the last lecture this semester, students were warned, the judges came to work. And they have not disappointed. I don't call team number 4 to the stage. Team number 4. Team number 4. Faculty mentor, Dr. Wei Chang Lin. Alumni mentor, Mr. Christopher Tarafa. And the project is sponsored by Sigma Scientific. Project manager, Rose Sherry. Team members, David Elalouf, Hila Goldsmith, and Natalie Sanchez. Let's give it up for team number 4. Is this your?
Oh, yes. Good morning, everyone. We are Team 4, and today we'll be presenting our project, the Multispectral Illumination System for Enhanced Endoscopic Imaging, or MISI for short. I would like to begin by explaining the procedure that our system was designed to enhance. This animation demonstrates a uroscopy, which is a minimally invasive procedure that involves the examination of the upper urinary tract. During this procedure, a ureteroscope is inserted into the urethra, through the bladder, and into the ureter. This allows physicians to directly visualize the urinary tract and also to collect any biopsies of suspicious tissue without making any surgical incisions. Upper tract urothelial carcinoma, or UTUC, is a rare but aggressive cancer that affects the lining of the renal pelvis and ureter, and it accounts for about 5 to 10% of all urothelial cancers. This is a diagram of the progression of a UTUC lesion. It starts off very small and difficult to visualize, and this is why early detection is critical in order to improve patient outcomes, as the faster that we detect any possible cancer, we could stop the progression for it to progress into the deeper layers of the tissue. Having a missed lesion is a very significant consequence. Up to 60% of UTUC lesions are already invasive at diagnosis. This can lead to an increased risk of metastasis, infection, kidney failure, and even lower survival rates. Current imaging modalities include computer tomography, which is non-invasive but has issues detecting flat lesions, white light uroscopy, which has direct viewing but also struggles with having limited tissue contrast, and lastly, narrowband imaging, also known as NBI, which does have enhanced lesion visibility. However, it requires specialized equipment that is very costly. Early UTUC lesions are flat and subtle, which make it very difficult to distinguish with the surrounding healthy tissue. This is why when we use white light uroscopy, it has very limited tissue contrast, and up to 25% of abnormalities are missed during the procedure, which delays diagnosis and treatment. Beyond the clinical need, there's also a growing business demand with a 6.8% compound annual growth rate for advanced endoscopic imaging systems. With a low-cost multispectral imaging system, we can reduce the reliability of expensive proprietary technologies and also expand the access to advanced imaging to hospitals and smaller hospitals and clinics. These are the challenges that motivated the development of our MISI prototype. MISI is a multispectral endoscopic imaging system that combines multi-wavelength illumination as well with our interface. We have features such as real-time image acquisition, narrowband image processing, adaptive brightness control, and region of interest detection. We chose to do multispectral imaging because we wanted to focus on the way that hemoglobin interacts with light.
Cancerous tissue contains more hemoglobin than healthy tissue, and by using blue and green wavelengths, we were able to increase the tissue contrast and therefore be able to have better visualization compared to just white light imaging. Now I'll pass it on to David to discuss our design table.
Thank you, Natalie. So now that we addressed the clinical need, we honestly wanted to make our design inputs reflect that need. The first one being our distal tip measurements. We wanted to make sure that we maintain a 3.9 millimeter with a tolerance of positive for minus 0.1 millimeters. Even though our system can be applied to any endoscopic system, we wanted to make sure that our application was for uteroscopic applications. Next is our wavelength ranges. The first one, we picked ranges between 460 and 520. The reason for that being is we wanted to target the absorption of optics when it came to deoxygenized and oxygenized hemoglobin. Our last thing is our temperature. We wanted to make sure we didn't exceed 43 degrees Celsius to make sure that no damage is done to the distal tip, as well as any patient undergoing this procedure. So that brings us to our first design concept. This allowed for uniform white light, but the biggest issue that came with this is that since we're dealing with a really small distal tip, those white LEDs all the way in the back were very small and very difficult to place. So that brings us to our second design concept, which comes with a more tapered size and allows for better anatomical access. However, when it came to 3D printing our distal tip, it came with a lot of issues since it's so tapered. That brings us to our MVP, or a more smaller design, which has simplified geometry and it has the benefits of this design concept number 1 and design concept number 2, but now we are able to print it for that simplified geometry. And now, and then we can pass around the prototype replica. That is a replica of our prototype. So it has our blue LED, our white LED, and our green LED with a central camera connected to our distal tip, and that distal tip is connected to a PTFE tubing. So this is our generalized system overview on how our device works. Our laptop is powering our device as well as powering our camera, and our Arduino Uno R3 is what's controlling our LEDs with our software connected to our laptop, and then ultimately image analysis and image staging. That brings us to our first simulation, so we wanted to make sure our device is able to work. So with this first simulation, we did an optical simulation to make sure that our LEDs were actually picked up by our camera. So in this simulation, we're doing a urinary tract. It's replicating a urinary tract to make sure our cameras are detecting our LEDs. And from our results, we were able to detect the LEDs with our camera, with all our LEDs. That brings us to our thermal simulation. We wanted to make sure our device didn't exceed 43 degrees Celsius on our distal tip, even though some of our distal tips or some of our LEDs were getting close to that threshold, we were still within our tolerances. That brings us to our Arduino setup. This is how we set up our Arduino so that it connects to our software and allows for it to work. And now here is a more in-depth electrical schematic that we made on KiCad. Here you're able to see that our Arduino Uno R3 has power going through all the LEDs through PWM pins 3, 5, and 6. That is what allows us to individually control our LEDs. Now, this is our main graphical user interface. So when a person is using this, they will be able to, this is what they will be able to see. Now I'll pass it on to Rose, who will go more in depth into our GUI.
Thank you, David. So there are two main workflows in the user interface, the LED controls and the camera controls. The user begins by testing the LED connections, then they can turn on the white LED with the option for automated brightness control or manual brightness control. Once the user finds a region of interest, they can then prompt an NBI image capture. They can see the changes here on the live camera display and have access to basic camera controls. Under white light illumination, the program also highlights redness and edges where an NBI capture may be useful. When an NBI button is pressed, it takes 3 frames in sequence, the white illumination for a reference, and blue and green frames. To result in the contrasted image there, the blue and green frames are processed. First, they're converted into grayscale, then the brightness values of their pixels are stretched to finally combine into a false color image composite. This is all to make the vasculature appear dark compared to the tissue background. Moving on to verification testing. Our device passed all 6 tests that we made.
including the criteria for LED spectra, thermal performance, and image contrast. We started off by making sure the blue and green LEDs outputted the desired wavelength ranges, and we also checked that their wavelength distributions did not overlap. The next test we did, because the LEDs in the cameras are compacted into a small distal tip diameter, we made sure that the temperature of the distal tip did not exceed over 43 degrees Celsius for thermal safety. Finally, the killer test of our project, thank you, David. The killer test of our project compared the contrast of white light images versus MBI processed images. And we measured the contrast to noise ratio on an optical phantom that mimics the absorption peak behavior of hemoglobin specifically at 560 nanometers. The result was that the MBI processed images showed an improvement compared to its counterpart of a contrast to noise ratio of over 5. This shows that our device does indeed provide high contrast visualization. Now I'll pass it off to Gila to explain the impact of MISTI.
Thank you, Rose. So when it comes to our manufacturing impact, our prototype cost was approximately $560, which was well below our $1,000 budget, mainly due to the fact that we did use a lot of in-house manufacturing, especially when it came to our 3D printed distal tips and integrating our off-the-shelf commercial components for our LEDs, our camera, and our PTFE tubing. Our device also proves to have many financial benefits, and because it does support earlier detection rates, it can possibly reduce the late stage causes that UTUC has, and lower the implementation costs for hospitals if they already do have existing endoscopes that use blue, green, and white illumination systems. On the global scale, 80 to 160,000 new UTUC cases happen worldwide each year, and in some of these regions, they do have limited access to advanced imaging modalities, so a cost-effective prototype would help them gain and improve access to it. Although our TOE MISTI is a prototype at this stage, for future commercialization, it would likely be regulated as a Class 2 FDA medical device through the 510K pathway, and it must demonstrate safety, performance, and substantial equivalence. The engineering standards that help guide us along the way for our design process and verification testing include the ISO 8600 for the requirements of medical endoscopes, the IEC 6061 to ensure electrical safety, and then the ISO 10993 for the biocompatibility of the materials we use and our future integration as well. Now, although our patent research has found that while MPI and multispectral imaging do occur, our innovation is the complete imaging software workflow that we have. As you can see here, it includes our white light reference images, our blue and green illumination capture, as well as our false grayscale composite generation. This offers the highest opportunity for future IP protection. When it comes to our future work, we would most likely integrate clinical materials, especially for our distal tip. Instead of using PLA, we would use PEEK. And for hardware miniaturization, instead of an Arduino breadboard setup, we would create a custom PCB, as well as the integration of artificial intelligence to help clinicians with lesion classification after a procedure is over. To conclude, UTUC is a rare and aggressive cancer that is very hard to detect using white light uroscopy, and to address this, we have developed MISTI, which does prove to have early detection rates and lesion and tissue visualization. Thank you to our professors, mentors, and sponsor, as well as everybody here in the audience today for listening.
Questions, judges?
Oh, did a great job, team. Great job, team. So you guys mentioned that you used PTFE tubing for your why was the PTFE material used? And was there any factor as it relates to wall thickness, diameter, around why that diameter was selected? Give us a background on that.
Thank you for your question. So we selected PTFE tubing because of the flexibility and also the diameter size of a ureter has the maximum constraint of 4 millimeters, and that was the perfect size. And it also can be biocompatible if we include a coating. So we wanted to make it as close as possible, like to an accurate prototype with that material selection.
I wanted to add one more thing. PTFE also has a low coefficient of friction, which allows us to also like easily slide into the cavities.
For your imaging, right? Did you guys consider using AI as part of your image analysis as part of the device?
No, we did not. We used an algorithm.
My question was in regards to the temperature. It did reach towards the upper limit. In your testing, did you test it with the automated brightness only or the manual?
So we did test our heat resistance when they were at full brightness. So then when it's automated, that's gonna be like the highest it's gonna go.
Thank you, team. So regarding like clinical and market need, could this technology be expanded to other areas that are not urethral? Like why is it only specific to urethral?
Well, our system is basically, we applied it for uteroscopic so that we have a device that we can make, but our main thing is our imaging system, which could be applied to any endoscopic system.
Okay.
Yeah, so also, our proposed solution was for uroscopies, but if you want to expand this, let's just say for a colonoscopy or any endoscopic imaging, you can make the distal tip bigger if you like, you can make it smaller. As long as there is the same optical geometry around our distal tip, and we use white, blue, and green illumination, this can be adapted for any other imaging modalities.
And then my other question is, how do you guys think this would perform under like other types of like real debris, like blood, things that can, you know, come in contact with?
So as our device stands right now, there is no working channel. If one of our future works to consider is maybe decreasing the size of the components of the LEDs if possible, and incorporating a working channel where blood and things like that can be drained or suctioned out. Also having maybe certain like sealants that covers the LED apertures and the camera apertures, making sure that those fluids do not go into the microscopic holes inside the distal tip.
Thank you.
So right now it's only detecting a mass. It's not necessarily that it has to be cancerous, right?
Correct. Yes, it's specifically detecting the vasculature of the tissue. The doctor is what discerns whether or not that may be concerning.
And there's no test? Are there any tests to detect it? Detect if it's cancerous or not?
Can you clarify that?
So basically it's like, how do you know it's cancerous?
So that would be based on also our future work. When we wanted to integrate artificial intelligence, it can help us integrate and have a lesion classification. For now, we are just checking the hemoglobin concentration when you're going into the uterus, so to see if there are any masses that are under the tissue as well. So for now, this is just up to the clinician to decide.
So basically, our device makes the blood vessels and those structures appear darker, increases the contrast so that the doctor can easily see the structure of those lesions that they're looking at.
Okay, thank you, team number 4. I now call team number 5 to the stage. Team number 5. Integrated endotracheal suction system. And the faculty mentor is Dr. Emmanuel Mora, alumni mentor Jennifer Mokeen, and the project is sponsored by Respirasense. The project is managed by Johan Gonzalez, team members Elena Gonzalez, Dario John, and Alejandra Fernandez.
Dario John with Team 5 and Respira Sense. Before I begin, I have one question for you. I want you to think about how many times in a day you have to clear mucus from your throat. It's probably not something you have to think about just because it comes naturally to you. Unfortunately, for intubated patients, this does not come naturally to them, causing mucus to build up in the endotracheal tube. So today we're going to talk to you about our solution to this problem. Take it away, Joan.
Thank you. And our solution to this problem is an integrated endotracheal suction system, brought to you by me, Joan Gonzalez.
Alexandra Fernandez, Elina Gonzalez, and Dario John.
So let's get right to it. So here's our agenda for today. And what is endotracheal intubation? Endotracheal intubation is a life-saving procedure used in respiratory medicine, used by 50 million patients worldwide. However, while they're very good at secreting and taking out mucus, sometimes physicians can't see what's really going on. And as you can see in this picture, sometimes it leads to clogging and ventilator-associated pneumonia cases. Not only does this drive financial costs, but also increases the time that patients are in the hospital. I'd like Alina to further demonstrate how this is a problem.
Thanks, Johan. Emergency intubation creates a substantial economic burden for healthcare systems. The global airway management market is valued at approximately $2.8 billion, and complications from difficult intubations can add approximately $20,000 to the cost of care for a single patient. By reducing these complications, our device has the potential to improve patient outcomes while also lowering healthcare costs and serving as a practical process improvement tool for intubation procedures. To translate this into clinical practice, future milestones will include an FDA 510(k) pathway, early clinical adoption, manufacturing scale-up, and eventual expansion into the market. However, the value of our device extends beyond its commercial potential. Although hospital resources and clinical workflows vary worldwide, patients requiring mechanical ventilation often face many of the same secretion management challenges. When designing our device, we considered different stakeholders such as physicians and respiratory therapists, taking into account reliable clinical performance, ease of use, and patient safety. Now I'll pass it on to Dario, who will talk about our MRs and the eyes.
Thank you, Alina. So we came up with several design inputs to match the market requirements that we deemed important for this device. Firstly, we wanted to look at the visualization of using the camera. We needed to ensure that we had at least 90% unobstructed field of view throughout the operation of the device. Next, we focused on the effective secretion removal and irrigation, ensuring that it was operating at safe pressures. We also wanted to look at the controlling of the distal tip and how that navigates the tube. And finally, we needed to ensure that this device was FDA and ISO compliant, focusing on biocompatibility, risk management, and also ensuring that it was compliant with the FDA 510(k) pathway for a Class 2 device. So what we came up with was a catheter that can perform 4 different functions. It's capable of visualization, suction, irrigation, and navigation using a distal tip. You might be wondering, okay, well, what's so special about this device? How is it novel? I've made it very easy for you. Here you can see that I've shown you other modalities available on the market right now. Our prototype is the only one that's capable of all 4 functions: visualization, suction for secretion removal, irrigation, and control using the distal tip. So we address the problem of mucus building up in the endotracheal tube. Our solution is to integrate a camera with an LED with automated suction and irrigation for targeted secretion removal. This is going to happen continuously with continuous visualization. Now I'm going to pass you on to Alexandra, who's going to discuss our design progression and how we chose our MVP. Thank you, Dario. So as you can see in this slide, we have the design progression, basically all the designs that we worked through these past 2 semesters. All these first 3 designs, we have 3 different handles. We have some bottles to activate suction and irrigation, some triggers to activate the irrigation system as well. And one of the main difference of these specific concepts was the lumen design, or the catheter design. In the first one, we have 2 internal channels, one for irrigation, one for suction, inside an outer catheter shell. The second one was a concentric design, and the third one was just one catheter divided into 2, one for suction and one for irrigation. However, we ended up with our MVP, our most valuable product, which I'll explain further. One of our major trade-offs when we were just picking the right design was also making sure that we're picking the right size of the catheter. Because one of the main things is fitting all these compartments and also being able to be safe for the patient when it's being just when they're being intubated, right? So one of the main things that we considered was just the high impulse model. In this case, This just relates to the resistance, which is inversely proportional to the radius to the floor boundary. This means that even a small increase in the radius of the catheter shaft just represents a great improvement in the suction flow and irrigation flow, which is our main concern. That's how we ended up with our key parameters: a catheter side with an inner diameter of about 16 French, which is also translated as 5.5 millimeter diameter. And suction and irrigation just shares the same catheter shaft. You can see this picture right here. We have the detailed design. The picture on your left is just a physical prototype, as you have it right in front of you as well. We have the 3D printed handle. We have the catheter shaft. We have the joystick and some electronics inside the 3D printed handle as well. And the two inlets, the one for suction and one for irrigation, these are being connected inside the 3D printed handle with a wide tubing connector to have one catheter shaft that's able to save the space and provide fluid management effectively. And we're able to just provide these four functions: articulation, weight control, clear visualization, and definitely effective fluid management. Now I'll pass it on to John, who will explain to you how we brought these ideas into life in our manufacturing approach.
Thank you. So as you guys can see here right in front of you, we use different materials. We use PETG as our method for the handle. Not only is this very, very rigid, but also is very cheap and easy to prototype. Additionally, for our catheter, we use PVC, which is used for flexibility, and also not only that, it's biocompatible as well. You guys can see right here with our electronics, we have some that were integrated inside, mostly the most vital ones like the articulation, and the ones on the outside for verification like our Arduino assembly. Now, we divided this all to different phases because, as you guys may know, this is an integrated system. First, we had our suction system, which composes of a vacuum pump, a canister. For our irrigation system, we had a water reservoir, a saline bag, and a pressure pump. For our camera, we use an OBM 6946 camera, which is one of the world's smallest cameras. In addition to that, it's very good for capturing information. And finally, for our articulation system, we had servo motors, joystick, and then some steel wires to pull out the end of the catheter. So we realized there were some things that did work and some things that didn't work. As you guys are figuring out and playing with the little handles, you guys can see that some of the designs were either too big or too small, or sometimes they didn't even have compartments. And we realized that we were able to change them because we either had some spacings to hold up the motors, for example, or for our lumens, some of them were either too big, so we had to adjust them to a smaller size, and having an adapter as well, it allowed for the flow of fluid, whether it was suction or irrigation, to happen. But in order for all this to work effectively, we need to verify it. And I'll pass it back to Alexander, who will share more.
Thank you, Joan. So in our verification testing, the main thing that we were looking for was having reliable electrical operation for at least 10 minutes, and also a camera visualization that was able to be not interrupted for at least 5 minutes. And this was able to be tested to allow troubleshooting while our entire prototype was being integrated. Also, one of our main concerns was able to remove 5 millimeters of mucus, simulated mucus, within 15 seconds, which was our target, and we ended up removing this amount of mucus in 8 seconds, which was great. And finally, one of our main results that we're still working on is the camera obstruction, because we have noticed that with high viscous simulated mucus, sometimes the lens is partially obstructed. This is our picture of our entire complete setup. Also, you have it right in front of you. On your left, you can see just the computer running with the code. In the center, you have the articulation subsystem with a breadboard, buck converter, power supply, and also right here at the lower left, we have the 3D printed handle with the catheter shaft. Now, then I will explain to you our suction and irrigation pathways.
Thanks, Alex. For the irrigation subsystem, we have a saline bag enclosed within a pressure bag acting as a fluid source. A submersible pump delivers irrigation to the distal tip through its dedicated lumen, allowing saline to flush out mucus and any other secretions from the camera's field of view. For the suction subsystem, we have an external vacuum pump acting as a hospital wall vacuum source. And the suction pathway includes a pressure regulator, buck converter, collection canister, and dedicated tubing that runs through the handle and catheter to the distal tip, allowing the airway secretions to be aspirated while the collection canister protects the vacuum from contamination. The interface shown here displays what we use for real-time monitoring of the integrated system. The OBM 6946 feed is on the upper left corner, and the calibration panel is below it, which allows you to adjust the camera settings to optimize your image quality. The upper right has the articulation geometry that we use based on the joystick's input, and below it we have the irrigation and suction rates being tracked.
So now, might as well show you guys how our setup is working. So right here, we have our mucus analog being collected by our handle. It's being collected to our canister. Not only that, you guys can see the camera right now working live. And you can see with the articulation, once we move the joystick, it just where the camera is located. And you can see where the mucus is being collected. Additionally, alongside the catheter, you have a syringe, which allows to inflate a cuff, which is used along catheters, and also allows it to maintain stability in the trachea as you perform this procedure. So now we'll talk about our accomplishments.
Thanks, Bjorn. So throughout the project, our team completed most of the major design phases. We first began with clinical and market research to identify a problem. Then we established our market requirements and our design inputs, evaluated several design concepts, and arrived at our MVP before fabricating, integrating, and verifying our prototype. Now I'll pass it on to Zaria, who will talk about next steps.
Thank you, Alina. So as you can see, we have come up with quite a complex prototype, but there's definitely room for improvement. The first one we want to focus on is improving the portability of this device. Right now, it's spread across this board, which is not compatible in a clinical setting. So that's the first thing we want to focus on. Next, we also want to refine the flow control so that we can have more variation when it comes to the pressures used for irrigation and suction. Next, we want to look at the visualization with the camera, just because right now, with higher viscous fluids, the visualization is not as good as it should be. And then later down the road, we want to look into in vivo testing. This could drive our costs up, but we want to counteract that on the back end by choosing materials that are still FDA and ISO compliant, but are more suitable for repeated cleaning cycles. So that's all we have for you right now. I just want to take this moment to thank our sponsor, Respirasense, our advisors, and our proposal committee, all of whom made the success of this project possible. We'll now take any questions at this time.
Great job, guys. So I have a couple of good comments. So one, the presentation was done really well, like the visual, keeping it clean and simple makes it very easy for someone that is not a part of your project to understand. Especially when you go into your career, that is very much recommended when presenting to big parties. I like that your product satisfies multiple clinical needs, so the suction, irrigation, secretion, visualization, all of that, so I think that's really good. And then the fact that the product can be integrated into like existing clinical workflows makes it a lot easier of a sell and an easier way of like integrate it into what they already do right now, the nurses and any other technician that's coming in to support the patient. So I think those things are really great. So how, I think you touched on this a little bit, but how would the design ensure that you don't affect the airway when you're putting it inside? Is it like nurse specific, like with training, or would the design help this?
So one of our main concerns when we were just discussing, first of all, our parameters was just making sure that the diameter was safe for the patient. Sometimes patients are being intubated, especially this specific device, we're trying to address it right now at the moment to adults due to the trachea side as well. So our main idea was basically making sure that we have, as you can see right here, this endotracheal cuff. That is the standard system already working on the clinical workflow, and just making sure that the sites is not affecting either the anatomy, and therefore is also being able to be integrated with other clinical workflows. So that's basically what we're working for. Making sure that the sites is good for the patient, first of all, for their anatomy as well, and second will be, we are looking forward to just decrease the size later in later iterations.
Okay.
Thank you for your question, of course.
Is the camera this black thing in the second and smaller too?
Yes.
Okay. So that answers my question. So since that answers my question, I just want to say I love how you went through the different design phases with the handle. It is this one's a little big, so I don't know how to work with it. I have my hands. But I know you guys are gonna, keep working on it, but that's the whole point of, going through process design and understanding how it's gonna work with the healthcare provider. So great job on that.
Thank you.
Great job, team. Just a quick question. One of the risks that you identified was the vision system working in different viscosity. What were some of the mitigations that you guys evaluate as part of that to mitigate that risk?
So right now, what we're looking into, like remember I mentioned later on the visualization, we want to look into using an anti-fog coating. But for right now, we did do some verification testing with lower viscosities, just to see how the camera would operate using our mucus analog hair, as you can see. And those ones were successful. So it's when we get to thicker, like the thicker mucus, which those are more, you see that more with like very extreme cases, but for like typical intubation cases, we're within that range of viscosity that it would function well.
So when we did these trials, the first trial we did was with water, food coloring, acrylic paint, and sanding sugar, and we got it to be like a viscosity around like 2 Pascal seconds. And then when we did trial 2, we got the same ingredients from trial 1, but then added the blue xanthan gum and jello powder, and we got it to a target viscosity range of 9, but we hope to increase it for the more extreme cases.
Okay, all right, thank you very much. A bit of housekeeping. After Team 6 presents, we'll take a 5-minute break, and then we will continue. So I now call Team 6 to the stage. Team 6, Knee Hero, Pediatric Knee Extension Rehabilitation System. Faculty mentors are Dr. Angoli and Dr. Assad, Dr. Mirza, and the alumni mentor, Sophia Mendez-Cruz. And the project is sponsored by Nicole Wertheim, College of Nursing and Health Sciences. The project is managed by Ms. Juliana Pacini Mesa. Other team members, Heaven Michelle, Sawyer Herman, Sophia Martinez, and Calvin Larkin. Let's give it up for team number 6.
Good morning, everyone, and thank you for being here. My name is Juliana, and I'm here with my team members, Sawyer, Calvin, Sophia, and Heaven. And today we will be talking about Knee Hero, the Pediatric Knee Extension Rehabilitation System. So meet Timmy. Timmy is 12 years old, and he grew up playing soccer around his brother, so soccer is a very important part of his life. When Timmy was playing a final match for a regional tournament, he made the bold move to fake out a defender. However, he suddenly heard his knee pop, and he collapsed on the field. Hours later, his worst nightmare became true. He had torn his ACL. But Timmy is not alone. If we talk about pediatric ACL injuries by the number, Timmy is just 1 out of 30,000 children who experience ACL injuries every year, with the majority having to undergo ligament reconstruction surgery just to regain knee motion. However, surgery is only the beginning, as the rehabilitation process can put them at risk of developing a knee flexion contracture, which is when the knee is stuck in a bent position and cannot fully straighten due to muscle atrophy or scar tissue formation. Even a very mild contracture of 15 degrees can increase loading at the joint, force the surrounding muscles to overcompensate, and cause the kid to walk with their knee bent, which is known as a crouch gait. If this complication is not treated promptly, it can progress into a deformity that can become harder and harder to treat. And this is no longer about a kid who's going to miss the season. It's about a kid who may lose the ability to walk properly, stay active, and return to life as they know it. Unfortunately, this is not rare. Around 2,000 children develop this complication every single year, which translates to about 5 children every single day. So, how can we treat and prevent this complication? So it starts with at-home static progressive stretching, which is the standard of care for treating a knee flexion contracture. So the knee is stretched into its L range and held in that position. And as the tissues relax, the stretch is gradually increased in order to progressively regain knee motion. However, recovery is not only physical. Around 34% of patients experience depression after an ACL injury, with emotions such as isolation and loss of aesthetic identity, making it harder to stay consistent and motivated with recovery. This is why treatment can not only focus on regaining knee extension, but also on the psychological side of rehabilitation. Therefore, the second step of an effective treatment must focus on promoting patient engagement with therapy. Without meaningful feedback or engagement, therapeutic adherence rates fall below 50%. However, with at-home gamified therapy programs, adherence increases to more than 80%, which means that the child is not only more engaged with therapy, but they have better functional outcomes and ultimately suffer less. The child, however, is not the only one affected by an ACL injury, as this can pose an immense financial burden on the entire family. Reconstruction surgery alone averages around $30,000, with mandatory at-home physical therapy adding another $1,800. And if the child develops a knee flexion contracture, then the family must opt for additional physical therapy or an at-home stretching device that can add another $1,800 in just 6 months. So what started out as a simple injury now became a very long and strenuous road to recovery. So in order to understand why these challenges persist despite the current treatments, my teammate Sawyer will now discuss the current rehabilitation landscape.
So now that we've seen the challenges that our pediatric patients face, let's take a look at the current rehabilitation options. Successful pediatric therapy relies on 4 key requirements: controlled extension, angular feedback, patient compliance, and a patient-specific fit. Weight-assisted knee extension devices fail to meet all 4 of these criteria. Serial casting is customizable, however, it does not allow for controlled extension or measurable angular feedback. Dynamic extension splints do provide controlled extension, however, they are still lacking in angular feedback, comfort, and meaningful engagement. Physical therapy alone is highly individualized, but does not allow for controlled extension or measurable therapeutic progress once the patient leaves the clinic. So all of these current rehabilitation options address part of the problem, but none address all 4 key needs. So we identified an opportunity to combine all 4 key requirements into a single rehabilitation system. So we set out to create an affordable, at-home static progressive stretching system for pediatric patients post-ACL reconstructive surgery that focuses on patient engagement, a patient-specific fit, and measurable therapeutic progress. Our goal is not just to restore knee extension, but to make therapy more engaging and accessible for patients completing rehabilitation at home. These goals are then translated into specific engineering requirements. Most critically, the device must keep the rate of angular adjustment below 0.5 degrees per second to keep stretching controlled and safe, and the device must remain at a low grip strength to use in order to remain usable for children. Additionally, the device must facilitate pediatric engagement with therapy to improve functional outcomes over time. The device must also remain at the set angular position within a 2-degree tolerance, and it must accommodate the varying leg dimensions of the intended population of children aged 12 to 17 years old. Finally, the device must facilitate measurable therapeutic progress and integrate the kinematics of the device with engagement and angular feedback. So throughout this design process, we reference engineering standards, including those on usability, orthotic design, and pediatric sizing to ensure that Knee Hero was designed to be safe, effective, and clinically relevant. So now that we knew exactly what Knee Hero needed to do, the next step was to translate these requirements into a practical solution, which my team member Sophia will discuss next.
To translate the clinical requirement into a mechanical solution, our design process began with the bowstring-inspired cable tensioning system. We determined that the angular adjustment speed needed to be controlled at the dial while also keeping the required grip strength low. So a few ideas were considered. First being a ratchet with fewer teeth, but it could wear down over time. Next, a torque-limiting slip clutch was also considered, but it was too bulky and costly. Finally, the gear ratio system was chosen because it winds less cable per turn, making the angular adjustment slower. Now, we also thought, how can we lower the required grip strain? We thought of a few ideas. The first one being a guided spool to reduce cable stacking, but it was too difficult to manufacture. Next, a cam spool was also considered, but the cable could slip, causing inaccurate cable adjustment. Finally, the gear system was once again chosen because it lowers torque, making the angle adjustment slower, while also making the dial easier to turn. Now, we concluded that angle locking can happen at both the hinge and at the dial. We concluded this by using a wheel to 10, but it was too bulky. Next, a pin and pull mechanism was also considered, but the user would need to manually readjust the pins, making it less convenient. Finally, a ratchet dial was considered because it combines both self-locking and angle adjustment into one single mechanism. Now, this is Knee Hero, our solution to improving pediatric rehabilitation after ACL reconstruction. At its core, it's a static progressive stretching device that helps children safely and gradually restore full knee extension. But this device is only half of the solution. Without engagement, our device falls short. That's why Knee Hero is not just a device. It's a complete rehabilitation system. So we integrated an application that includes real-time angular feedback, interactive mini-games, and encouraging visuals to make therapy more enjoyable. We also included pain check-ins so the child could communicate their voice while also giving the physical therapist the progress checks they need. Knee Hero addresses both the physical and motivational challenges of therapy and
and combines both a digital experience with a mechanical solution. Now I'll pass it to my team member Calvin to discuss the mechanical simulations.
Prior to manufacturing sync component, simulations had already validated the design. A 42.5 Newton strap force was assumed even at the leg, which poses no hotspot and just comfort. Under a maximum therapeutic load, the hinge stress remained well below the material strength, in which is confirmed that the device can withstand safe forces, session after session without failure. To test durability, we simulated a waist-height drop that represents a realistic worst-case scenario for everyday use. The stress remained well below the material strength, in which is confirmed that the device can withstand, in which knee hero can withstand accidental drops and keep working. In addition to manufacturing knee hero, it consists of 3 builds: the dowel housing, lifting with adjustability, and the circuit assembly. Once completed, they are assembled, and once the circuit housing is attached to the thigh component, and the angular tracking magnet is attached to the hinge. Now that our prototype is assembled, I'll hand off to my next team member, Heaven, to discuss how knee hero can perform in the real world and verifications.
Our first protocol tested knee hero's accuracy and feasibility where it matters most: real world use. We benchmarked the encoder against a calibrated analog goniometer across 4 different knee positions, then pushed further, measuring angular drift under 15-minute therapeutic stretching loads and clocking its adjustment speed. All tests were conducted across multiple trials to ensure consistency and statistical reliability. Knee hero not only met its acceptance criteria, but exceeded them. All results demonstrated statistical significance, confirming that knee hero met all of its required specifications. This protocol tested knee hero under real therapeutic load. We measured hinge displacement and axis deviation to confirm that the device remained aligned under load, interface pressure to ensure that the device remains safe and comfortable, and peak grip shrink to confirm that the device's ratcheting mechanism can be adjusted with minimal effort. All tests were conducted across 3 trials. Knee hero satisfied every mechanical and safety verification with considerable margin. All metrics were evaluated against their acceptance criteria, and all its results demonstrated statistical significance, confirming that knee hero functions reliably and safely. We set out to build a device that is safe, functional, and engaging for pediatric patients, and these verifications prove that we have achieved that. Knee hero isn't just an idea anymore. It is a fully verified prototype ready to help children recover with confidence. But today's solutions don't solve every problem. So we didn't set out to build just another knee extension device. We set out to build a device that gives children everything they need to heal. That's knee hero. We're bringing that kind of solution to the market and understanding where it fits inside of the existing landscape. So I'll hand it over to my team member Calvin to discuss intellectual property findings.
Our patent source confirmed that staff progressive stretching is already well established. So the innovation isn't the therapy, it's delivery. Existing devices slowly focus on mechanical stretching, whereas knee hero combines therapeutic stretching, real-time angle tracking, and active monitors progress and therapy adherence. Knee hero is a proven therapy that meets modern technology. Knee hero fuses objective tracking, controlled extension, and personalized fit with recovery spins that kids want to stick with. Knee hero is more than a knee device. It's a scalable rehabilitation platform that is designed to expand across joints, personalized recovery, and evolve into a universal therapy app that supports physical, occupational, speech, cardiac, and other rehabilitation services. With that being said, I hand off to my next team member, Sawyer, to discuss how knee hero can move from development to patient care.
Throughout this presentation, we've talked a lot about Timmy. Although he is a fictional patient, the problem that he represents is very real. Our final prototype will be delivered to a pediatric patient at Nicholas Children's Hospital, where it has the ability to have a meaningful impact on a real child. What makes knee hero unique is not the mechanics, it's the focus on engagement. Therapy only works if children actually stick with it. By combining gamification and a user-centered experience, we're transforming therapy from something children have to do into something they want to do. So our goal is never just to restore knee extension, it's to get kids back to doing what they love. For Timmy, that's playing soccer, and for every single child like him, that is why Knee Hero matters. We would like to thank our faculty instructors, Dr. Christie and Professor Sharastani, as well as our faculty advisors, Dr. Angoli and Dr. Mirza. We would also like to thank our project sponsor, Dr. Amanda Thomas, as well as our alumni mentor, Sofia Mendez-Cruz, and some additional alumni who helped us on our journey, Annalyn Ramirez and Tizana Restrepo. We would also like to thank everyone here today for your time and attention. Thank you.
Was there any consideration given to existing technologies, maybe more adult, less use adults that you guys leverage as part of your design?
Thank you so much for your question. Yes, the current rehabilitation method that is used is static progressive stretching, and at its core, this device is a static progressive stretching device. So the knee is stretched into its end range and then it's held, and then as the tissues relax, that's how the contracture is slowly getting better. So that is the technology that we leveraged in our device. But the touch that we added in order to keep in mind our audience, which is pediatric patients, is the fact that if they don't engage with therapy and if they don't feel like they are moving forward with therapy and feeling rewarded, then it can be a lot harder for them to stick with it. So we are providing the mechanical solution, which is already in the market with adults, but we're also providing that engagement side to help kids feel like that they're getting better and to help them feel more engaged and feeling like therapy is not something that they have to do, but something that they want to do.
Additionally, for adult patients, the reward is recovery, but children don't see cause and effect in that same way that we see it. So that's why the engagement is so important for children specifically, and why it's not integrated into adult devices in the market today, because it's not as necessary for adult patients due to that cause and effect and recovery being the reward for an adult.
So, 2 questions. 1, does it come with GTA 6?
Maybe your future consideration.
What safety mechanisms are built in for unsupervised use?
So there is a worm gear inside of the BOA housing in here, worm gear, that slows down the winding up of the cable. So we have a 1:60 gear ratio that makes it so that one turn of this dial that's right here makes it, one turn of this dial is only equal to 1/60th of the turn of the worm gear inside. So even if children wanted to move the dial extremely quickly, the device itself is made so that it's not possible for them to be able to go past that safety limit. And additionally, in the application, we have integrated the paint check-ins and the security system that detects also the speed at which the ankle is being adjusted, so that if they're going too quickly, the app will tell them, hey, slow down, you need to go slower because it is not safe for you.
My question is on the game. Is the game engaging and educating them on what's happening, or is it just a game? Like how is it linked to what would motivate them to want to do this with the game?
So right now, the game is not, doesn't have any educational games. The games that it has right now are very simple games that kids from the ages of 12 to 17 will play. At the end, we hope, like with different devices, or even with this device, that we can include like math games, so it ties into something that they could benefit from as well. The current games that are there, they level up with each session. So right now, if you start each patient gets a different planet that they land on, so it's completely randomized, and you can get completely randomized games as well. So once the patient lands on the planets, they do their session with their mini games, and they get stars. Those stars then can later give them the power up, so they can go into the next level, and the games get harder.
Okay, so when you go to their physical therapy session or their training session, that's when they do the game?
Yes.
Y'all designed the game as well?
Yes, it is.
The games are only accessible during the session, and it also tracks the progress as well, and so it gives motivation for that as well.
Okay, I thought it was just playing at home.
No. So the parent can actually log in and see what the kid is doing and what planet they're on, what degree they got, and same thing with the physical therapist. And the physical therapist can leave notes to the parents, and the parent can leave notes to the child, and vice versa.
Yeah, I just want to say good job at storytelling. It's she hit on some points with the last team about how it's important. Your presentation style, when you're talking to different stakeholders, different groups of more knowledge or less knowledge. So the storytelling that happens at the beginning is very engaging for the product, and that's very, very important. So good job.
Thank you so much.
I agree with that. Great job on this, Knee Hero. And I like that you guys are using a more modern technology. I do see that from where I work, where a lot of companies work, they're trying to find ways of integrating apps, AI, anything that you can, right? As technology is going a lot faster than the market is. So one question I have as a mom, a toddler, and things like they don't have phones, right? And we want to limit their screen time. Is there a way that they could use it too much, like overstretch their knee where it starts affecting them? So let's say if they use it for an hour, 2 hours, something like those types of controls, something that you guys are integrating into the app, not just like a physical mechanism of like you can't go beyond this angle, this amount, but like a time or.
So the app actually includes a 5-minute timer, and the physical therapist can change how long this therapy session needs to be. Right now, what I have programmed is that if the child does 3 sessions, 3 times a day for 5 minutes each session, and once they reach the 3 sessions of the day, they get like a little notification that says, astronaut, return to your base. You've completed your therapy sessions. Come back in a few hours.
Yeah, so the games are locked after the therapy is completed or when they're not doing therapy. And they also have the option to opt out of the game. So if they just want to do the stretching and not play the game, then they can decide that too. But the game is only to make it so that the duration of the session doesn't feel like it takes too long and it really hurts. And it's to make them feel like they're providing something to their therapy and that they're being part of their own recovery, while also keeping them engaged and make them enjoy the time that they have to stay in that stretch.
Awesome. Thank you guys. Great job.
Thank you.
We'll break for 5 minutes. Judges, if you want to take a break.
Excellent job. Excellent job.
I have the bag.
Oh, okay, okay.
Excuse me. And what tip is this? This is 7.
Yeah, my mom was Papa,
I can name.
Hey!
Yeah, very nice.
Okay, that's good. Thank you. Very good. Okay? Yeah. It's not very drastic. Your leave number is 8 or 9? 7. Yeah.
gonna have to be here a while. Get some coffee. Yeah, I saw that. Wow. Where's my picture? I'll go out. That's a good picture.
Mr. Herman. Pleasure to meet you. Nice to meet you. Everybody star here.
You go the same
That's you.
Good luck, man. You got it. Oh, yeah. Another show? Yeah, but that's what.
Okay, let's get started. We have team number 7 on the stage. Trocar's stabilization and positioning system. Faculty mentor, Dr. Hutchison. Alumni mentor, Alex Gugliarte. And the project is sponsored by Vulcan. The project manager, Jennifer Escobedo. Other team members, Aaron Morgan, Christine Smith, and Hugo Sinistera. Yes, Sinistera? Okay, thank you. Let's give it up for team number 7.
Good morning. My name is Christine Smith, and these are my colleagues, Aaron Morgan, Jennifer Acevedo, and Hugo Sinistera. We are Team 7. Our sponsor is Vulcan Manufacturing, and our project is the Trocar Stabilization and Positioning System, or the TSPS for short. So before we begin talking about our device has a lot to do with laparoscopic surgery, so we wanted to explain what that is. Laparoscopic surgery is essentially a minimally invasive surgical technique that allows for faster recovery time when compared to open procedures. This is a video demonstration on how it works, but before we begin, I did want to explain the first step called insufflation. Insufflation is when the surgeons inflate the abdomen with CO2, which will create more space in the abdominal cavity, as well as make the skin a little bit more rigid for
for trocar insertion. Then going back to the video, you can see that the primary surgeon inserts the trocar into the inflated abdomen and then is able to use the laparoscopic instruments. So as you can see from the video, the trocar plays a vital role in this procedure because it creates and maintains surgical access to the abdominal cavity and also allows the laparoscopic instruments to be used. There are 4 modalities used for trocar fixation. While they all have their own advantage of improving trocar slippage, they do have their disadvantages. For example, the threaded trocar and suture fixation methods affect the patient's soft tissue, which makes it unreliable for prolonged procedures. Additionally, the hastened trocar and radially expanding trocar are extremely expensive, which can make it unsuitable for medical institutions who may not be able to afford this method. All in all, there's not one modality for trocar fixation that addresses all of the limitations that come with trocars. Those limitations are that trocars can shift, tilt, loosen, or become unstable during the procedure. This can result in the surgeon experiencing limited mobility as well as muscle fatigue. Additionally, these limitations can result in interrupted surgical workflow. For example, if the trocar comes out, it needs to be reinserted, or if it loosens or tilts, it needs to be adjusted during the surgery. Therefore, trocar instability matters clinically because it can affect patient safety, procedure efficiency, as well as it can interrupt the surgical workflow. Uncontrolled trocar movement can result in repeated adjustments and reinsertions of the trocar, which can increase operating time as well as interfere with instrument handling. Therefore, due to that problem, our team identified a need for a stabilization device that can secure the trocar while still allowing controlled repositioning and maintaining unobstructed surgical access. Additionally, by the end of 2026, it is projected that 35 million laparoscopic procedures will have been completed. Of that 35 million, 25.6% of those procedures will result in a trocar needing to be readjusted or reinserted during the procedure. This shows clear clinical evidence that trocar fixation needs to be improved and shows a strong opportunity for our device, the TSPS. Our device is essentially an adjustable mechanical external support that stabilizes the trocar and allows for controlled repositioning during laparoscopic surgery. Key benefits include stabilization, adjustability, and it protects the surgical workflow. From a business standpoint, the laparoscopic instrument market is a global and growing market that shows strong opportunity for scalable production as well as an earning target of approximately 30 to 50%. This chart here shows the duration of common laparoscopic procedures. More specifically, it shows the average duration as well as the highest ever recorded duration of each procedure. These higher duration times can be attributed to the interrupted surgical workflow. Therefore, if by stabilizing the trocar, we will be able to reduce the amount of adjustments and reinsertions of the trocar, therefore reducing the operating time as well as saving hospitals and medical institutions that perform this procedure approximately $2,000 to $10,000 in associated costs. And now my colleague Aaron will talk further about the design portion of our project.
Thank you, Christine. So, beginning with the design portion of our process, we first defined the problem, and to do that, we used the design table as shown here. In total, we had 9 market requirements and 9 design inputs, but for the sake of brevity, we only showed the 4 most critical ones. Beginning with design input number 1, we first defined what trocar displacement is, which is 1 centimeter of movement from its initial position. And design input number 3, we defined what angular drift is, which is greater than 5 degrees of movement from its initial locked position. Then, with design input 8, we then defined what the minimum cycles of performance, which was 100 cycles before any failure or a loss of performance. And design input 9 was where we defined the amount of force our device must tolerate before any failure occurs. These were based off of standards from ISO, ASME, and IEC, which were used to ensure that our product maintained an effective and safe performance while also having an ergonomic design with proper dimensions and tolerances. After we defined the problem, we moved on to the ideation phase, where we referenced on-the-market surgical assistive devices to ensure new ideas were created. So after referencing these, we then created our design concept for two subsystems, beginning with the support arm design concepts, where we had the sliding arm, the gooseneck arm, and the telescopic arm. Then we moved on to the second subsystem, where we designed for the trocar interface, where we had the simple tight fit clamp, the Marmon clamp, and the lap style clamp. Out of these, we decided that the two best for each respective subsystem was the telescopic arm design and the lap style clamp arm design, which we used to create the trocar stabilization and positioning system. This most viable product was selected due to its reliability, its performance for stability and adjustability, while also maintaining ease of use for our customers and consumers. Now with Jennifer, who will be discussing the final TSPS design.
Thank you, Eric. So for the final design, we have a telescopic support arm, a vertical tube, an articulated ball and socket joint, and an interchangeable trocar interface. Now this design has a total of 9 components, 5 of which compose the telescopic support arm that has inner locking mechanism that allows for the repositioning of the system. Now, after this process was done with a manufacturing cycle that started with CAM modeling, then went to 3D printing, and then those 3D printed parts were verified for tolerance and functionality. The support arm has a total of 4 versions. The 4th and final version had 4 pegs and 4 inner releases that allow for strongness and support of the system. After the final design was concluded, we were able to do some simulations that allow us to know that the design was able to support laparoscopic forces. Now, this stress simulation shows that no stress failure of the system itself happened. Next, the displacement plot shows no displacement, minimal displacement of the system. And as for the factor of safety, the values were higher than 1, meaning that there was no structural failure of the system, allowing us to know that this design was able to support the laparoscopic forces. Now with Hugo and the design verification.
Thank you, Jennifer. Now moving on to the design verification testing. Here in this table, we have the 9 design inputs that we have tested for. And today we're going to focus on these main design verification tests that are critical to the functionality of our device. Moving on to the first one, we have the trocar stability and the load resistance test. Here in this test setup, we have fixed the trocar interface along different points of the cannula, and we applied 20 newtons of force utilizing a force gauge for 10 seconds. Here in this table, we see that the maximum and the average values are all below our passing criteria of less than or equal to 10 millimeters of displacement. Here in this chart, we're seeing the relationship between the initial position of the trocar interface and the displacement. What we are showing here is that no matter where the trocar interface is on the cannula of the trocar, there is no significant difference in the slippage of our device. Next, we have the angular drift. For this test setup, we used a laser pointer and we applied 20 newtons of force at the distal end of the trocar interface at 3 different angles. We utilized the equation here on the screen to calculate the angular drift of the trocar. Here in our table here, we can see that the averages at each point were 1.67, 4.14, and 4.24 degrees of angular drift respectively. These were all below our passing criteria of equal to or less than 5 degrees of angular drift. And you can see here in this table, we can see the averages at each point and our threshold, which we remain below for this test. Finally, here we have our durability test. So we simulated on SolidWorks utilizing the final material of stainless steel. We simulated 100 cycles of locking and unlocking of our telescopic arm, and we observed for any cracking or deformation of our device. As you can see here in the simulations, we have no significant damage or any failure of our device, which is a pass for this test. Next, here for our regulatory assessment, our device will most likely be a Class 2 device following the 510K regulatory pathway. This follows predicate devices that are patented on the market and commercially available. For our manufacturing costs, we estimated a final prototype cost of $1,755. This is with the final material, and please take in mind that this is for one singular prototype. Now with manufacturing production volume going up, the cost will likely go down substantially. And for a reusable device like ours, the cost per use will remain relatively low, and at a $2,000 to $10,000 cost avoidance for hospitals, we see a great financial upside for this device. Now here, this is our product life cycle. This is how we like to implement it to commercialization. Right now, we are at step number 4 after finalizing our concept for our prototype and doing our design verification testing. Now looking into the future, we'd like to optimize our mechanical components like our telescopic arm and our trocar interface and expand its compatibility with different types of trocars and different sizes. For our validation, we like surgeon feedback as well as simulated OR use and cadaveric testing. And finally, for commercialization, we need to follow the FDA regulatory pathways, include the final medical grade materials, and have sterilization validation for our device. So now, thank you for listening to our presentation. We'd like to thank our sponsors, our mentors, all the faculty, and everyone here present, and all these great people that helped us along the way. Thank you. Also, we have here a QR code if you'd like to scan for more information on our device. It is on the table. What they're gonna see.
Thank you guys. I like that the product is simple. It's not a fancy robotic system. We not reinventing the wheel here. It shows that something like this could impact, you said 25% of the cases that it would apply to, so it's massive. So how would this product accommodate like different size operating tables, different size patients? Is it something that is, that has that level of flexibility?
So for the tables itself, So for the tables itself, this is connected to a webcam that is standard. So these webcams are already in the market. There are standards, and the vertical tube is the size of support that attaches to these already in the market webcams. As for the trocar interface, we have right now only compatible with 5mm and 12mm trokers, because we only were able to get those two within our budget. But we wanna expand to the range of with 10 and 11mm trokers as well, which are also standard in these surgeries. As for different patients, this tube can be moved up and down. So for bigger BMI people, for bigger people, and inflated and patients, this could be moved up, and then it could adjust easily and it moves on the rail as well. So, yeah.
Okay. And then, I think there was a slide on this, but is it within the sterile field or outside of the sterile field? Do we have to go through a sterilization cycle after?
Yeah,
after surgery?
yeah. So when you first get it, it's gonna be sterile, and then it's gonna be made out of stainless steel that is going to go through the sterilization process.
Thank you.
I know you all went through different types of designs that you were considering for your MVP. Why did you go with the telescope design?
Well, this was due because it has a better stability than initially we thought about the gooseneck arm, which is like, one of the influences for our device was the Metaflex Flex arm, which it holds surgical instruments, but that doesn't provide the rigidity that we needed for actually stabilizing the trocar into place.
Okay, and then this top part here, this is able to be adjusted for different angles?
Yes.
Or once you position, like if the surgeon needs to move, he can do that, or the
Yes,
assistant
you
can do
can
that?
unlock the ball and socket joint, and you can position it at different angles, then lock it again. And the trocar piece is actually interchangeable. You can use it for different sizes of whichever trocar you need.
So we have here the number.
Okay.
That one is a 12mm.
Okay. I was, just because you guys are, you said it wasn't in your budget, it looks like you can adjust maybe the diameter is a little different, but you can use this or redesign it, maybe?
Yeah.
To just open up
Yeah, so
instead of, yes, exactly.
Yeah, so that's actually.
Yeah.
Oh, sorry. I'm so sorry. So that's actually one of our improvements. We wanna see if we can actually make out one size fits all. The problem is that for the so for this one, we were like, okay, let's make sure that we have something that stabilizes the system first, and then after that, we can improve upon this.
Just because in consideration for hospitals
Yeah.
purchasing different components is also a part of a sell factor
Yeah.
if you only have one, so.
And, good job, first of all.
Thank you.
So what's your proposed manufacturing process to make this?
I'm sorry, what?
Your proposed manufacturing process to create this device?
Well, the manufacturing process for this device is going to be manufactured out of house, so it's going to be mostly machining, CNC machining for the metallic parts, because this is all mechanical parts that these come separate and then come together. We can adjust it again together, so these are all parts that are going to be made nationally, probably, and manufactured with machining.
Then you said the load at the end doesn't affect the way it telescopes?
No,
No.
actually, no, it doesn't. Because of the way that, sorry. because of the way that the inner railing system was designed, the weight of the end, it doesn't affect at any of the distances that you put the scope at.
Okay.
Yeah.
I'm sorry, Professor. You can speak with them afterwards. Please feel free.
I have one more question.
Only the judges get to ask.
So right now, in the market, it doesn't exist for this with the whoever's making the ancillary equipment, like the laparoscopic device, they haven't made a plan for a.
No, this is not what
Yes, so current modalities for laparoscopic surgeries and assistive devices for such, they only include surgical robots, which they're either too expensive or there's nothing that accommodates for these type of situations. So that was one of the reasons why our group chose this project, because majority of these hospitals, not every hospital can afford a Da Vinci, for example. And those cost way too much, and we're considering for those out of country, or say third world country hospitals where they have to perform such surgeries, they can't afford these, but they still need help with the stabilization of their trocars to reduce their costs. So we decided that if we focus on a simple, cheap, but effective solution for these consumers to have.
I can absolutely see this as like an add-on to the people that are selling the equipment and all that, as something that comes with the package, being that there's 25% of, the market that complains about this. Thank you.
Thank you so much.
Thank you. And team number 7 is advised to meet with Professor Munir. Ladies and gentlemen, I present to you team number 8. Team number 8, low volume saliva collection device. The faculty mentor is Dr. Mirza, alumni mentor Ms. Natalie and Michael. The project is sponsored by Portable Diagnostic Systems and it's managed by Pablo Reyes. Team members Elizabeth Turner, Valentina Vargas, and Camila Barroso. Yeah. Let's give it up for team number 8.
Good morning, my name is Elizabeth. I'm joined here today by Pablo, Camila, and Valentina. We are Group 8, and today we'll be introducing our low-volume saliva collection device. Saliva is becoming increasingly popular in diagnostics over other methods that involve blood or urine because it is non-invasive, which encourages patient compliance, fast, and low cost. Saliva-based tests first require that a patient provides an oral sample that is collected and transferred into a diagnostic cartridge, producing a readable result. And this process has proven to produce viable results in diagnostics, which introduces the question that if this process has proven to function properly, what is the problem that we are addressing? The problem that we are addressing, isn't with the design of the devices themselves. It's that the devices weren't designed to accommodate for every population, with some of these populations including homeless, those that suffer from xerostomia or dehydration, elderly, and drug-using populations, where these individuals are typically unable to produce the sufficient saliva required for diagnostics. This gap is clearly demonstrated in current saliva collection devices that demand significantly more saliva than the minimum requirement of 20 microliters. And right now, there is no passive, low-volume collection device compatible with point-of-care use. This greatly impacts various populations, where roughly 22% of the population is impacted by xerostomia, and up to 47% of older individuals suffer from reduced saliva flow. So the question becomes, what is currently being used in saliva-based diagnostics? The current saliva collection modalities include passive drool, swab kits, and absorbent pad collection devices. And while they are typically fast, non-invasive, and low cost, they require anywhere from 0.5 to 1.5 milliliter of saliva for the downstream process in order to function properly. And as we previously discussed, some individuals are unable to produce this minimum requirement, bringing us back to our gap and highlighting the need for a low-volume saliva collection device that aims to collect a minimum requirement of 20 microliters. And this is where our device, Salvance, comes in, because ultimately reliable diagnostics should depend on how much saliva a patient is able to provide. Our solution is a passive capillary-driven collection device that doesn't require any external force or user effort. It's a low-cost, single-patient use device compatible with the portable diagnostic system diagnostic cartridge. We designed and verified a fully capillary mechanism, completed pre- and post-manufacturing verification tests, and completed a design history file in compliance with FDA and ISO standards. I am now going to pass it off to Camilla, who's going to further discuss Salvance and its development.
Thank you, Elizabeth. After identifying the problem, our next step was to identify design requirements that were needed to solve it. We came up with 3 key marker requirements. Our device needed to collect saliva from low volume saliva production individuals. It needed to maximize sample recovery and minimize sample loss during collection and transfer. These marker requirements translated into specific design inputs. Our device must collect at least 20 microliters using passive capillary action. It needs to maximize it needs to transfer directly into a diagnostic cartridge while maximizing sample integrity, and it needs to leave less than 5 microliters of residual sample after the transfer. With this requirements in mind, we started developing our design. We encountered 2 major design changes throughout the whole process. We first had a compression-based mechanism, saliva collection device that used an absorbent material to collect the saliva. However, after testing, we came up with some IP limitations. Because of this, we had to redesign, and we focused on passive capillary action. This finalized our final validated prototype. After this, our device is composed of 5 components. We have the top housing, that's the body of the device. Then the bottom housing that aligns and supports the internal components. We have the borosilicate glass capillary tube, that is the core of the device because it's where the saliva is going to be collected. We use borosilicate glass only for prototyping and verification testing. However, in future development, it can be changed for a more suitable material. We also have the silicone nozzle, that is where the saliva is going to enter the capillary tube, and the silicone O-ring, that is just for a leak-resistant seal. After this, we created engineering drawings, and here we have the assembly. We have an assembly drawing, and we also have an exploded assembly. We also did engineering drawings for each individual component. These include dimensions and specifications. Both of these are mainly used for manufacturing to ensure the device is manufactured correctly. We also created animations in SolidWorks. In the first one, we can see how the device is assembled. The silicone O-ring attaches to the top housing, followed by the glass capillary tube, then the bottom housing, and finally the silicone nozzle. The second animation shows how the device interfaces with the diagnostic cartridge after the sample is collected. In here, there's a video of how our device works. You can see the pink fluid sweeping off the capillary tube. And for a better demonstration, we have an image on the other side. After the design is done, I'm now going to pass it on to Valentina, that's going to discuss our simulations and verification testing.
Camila. Before manufacturing, we also did some simulations to confirm that our device would work. We first used Jordan's law to predict that the capillary rise was 23.4 millimeters, which confirmed that our capillary dimensions were appropriate. We also calculated a theoretical volume capacity of 84.82 microliters, which exceeded our minimal collection volume. We also conducted a thickness analysis on the housing and hustle to identify any areas that might be suitable for fabrication or handling. The results show almost uniform wall thickness, which confirmed that our device is suitable for fabrication. After performing all the simulations, we can move on to pre-manufacturing verification test. Verify the capillary collection, and then we verify the capillary uptake, dimensions, recovery efficiency, residual volume, were all tests met the acceptance criteria. We also did a compression test to evaluate the structural integrity of the glass capillary tube. The baseline applied 9.5 newtons, and as you can see in the graph, there was a little minimal deformation but no fracture. We also increased the compression test to 190 newtons to simulate an accidental bite force. Although there was a little more deformation, there was no fracture, demonstrating that the glass capillary tube maintained its structural integrity. After the pre-manufacturing verification test, we can move on to the post-manufacturing verification test. When we tested the prototype under real-world conditions, we verified the cartridge interface, stability, low saliva performance, where all the tests met the attendance criteria, as you can see in the graph. And then I can pass it over to Paulo, who will discuss more about the manufacturing and necessary costs.
Thank you, Valentina. So, after verifying our device, we evaluated its manufacturing feasibility and production cost. Our total material cost comes to be $4.25, and after accounting for labor and manufacturing overhead, the total unit cost is $7. Our device is expected to be regulated as a Class 1 medical device because its intended use is to collect and transfer the sample without performing an analysis. Throughout the whole design process, we guided ourselves based on international standards and medical regulations, guiding our material costs, guiding our material selection, and evaluating for biocompatibility, risk management, and quality management systems, as well as ensuring that we work with in vitro diagnostic workflows. Our minimum viable product demonstrates how we can fulfill all of our market requirements. We provide a suitable low volume collection device that minimizes sample loss with the use of passive collection, and we transfer it with a silicone nozzle directly to the portable diagnostic systems cartridge, minimizing loss and maintaining a simple and low-cost device. For IP opportunities, after demonstrating that we can have a successful device that fulfills all of our requirements, we evaluated the patent landscape, and we found that many of the current technologies use internal fluid reservoirs, sample absorbent collection pads, and volume indicators, and lastly, they use extending collector elements. So you may be thinking, how is Salivance different? Salivance provides an innovative design that uses passive capillary action to collect the sample, a soft silicone nozzle that provides flexibility and patient comfort, and lastly, it transfers it safely into a portable diagnostic systems cartridge. This opens the door for future intellectual property opportunities. For future opportunities, we want to upgrade our design and create a single-use, sterile, and disposable device with sterile packaging. We also want to upgrade our design by transitioning from prototyping to injection molding. This way we can provide scalable manufacturing. And lastly, we want to take our device all around the globe to underserved and resource-limited populations. We want to give special thanks to Dr. Hamid Mir, to Dr. Asad Mirza and Ms. Natalie Michael for their mentorship, to Dr. Michael Christie and Professor Hamish Harsani for their support, Claudia Estrada, and the whole biomedical engineering department. We want to give thanks to our sponsor, Glendon Simmons, Ty Gabriel, Maxwell Arts, and everyone at Portable Diagnostic Systems for trusting us with this project. Thank you very much, and we open the door now to questions.
Good job, guys. So, in this entire process, how do you basically maintain the integrity of the sample with the transfer from the capillary tube to the sample?
The diagnostic card, the diagnostic card, yeah.
In terms of like, evaporation or, something happening with the sample?
So because it's a direct transfer, it goes directly into the diagnostic cartridge, ideally right after the sample is taken. We have a silicone nozzle at the top that is intended to enclose the tip of the capillary tube, and then it just directly transfers. We didn't have any problems with compatibility issues when we were doing verification testing. We didn't notice that it uptook anything else other than fluid, or when we expelled it, that it didn't leak at the ends or not expel all of the fluid.
Maybe I missed it, but from a volume standpoint, how do you ensure that you meet the minimum 20 microliter volume?
We ensured that we met the minimum. We performed a simulation. We used Duran's law to kind of give us an estimate on what the diameter and the length of the capillary tube needed to be. And from that, we used the Fisher brand hematocrit capillary tube because it met and aligned, the material properties aligned well with what we were looking for, with the interior being hydrophilic, so we knew that it would uptake the saliva well. I'm sorry, could you repeat the minimum sample requirement? We performed the pre-manufacturing test, and we had a fluid sample within a bowl, and we uptook it and we measured it and then we measured the height and from the diameter and the height. We used an equation to measure how much volume was uptook, and from all our pre-manufacturing verification tests, I believe we got them average to be around 22 microliters.
From a user standpoint, how would a user know that you're meeting that minimum requirement? Is there like an indicator or something they will see?
There is no indicator. We did not take that into consideration when we were creating the device.
Okay? Oh.
Great job, guys. I like that it's simple and it's a passive capillary action and there's not like moving parts, right? That makes it more complicated than it needs to be. So how does it work? It just sits in the mouth until it reaches what it needs to?
Yes, the device is intended to go directly into the patient's mouth, and you need to keep in mind that our patients have dry mouth, teratostomia, or they have difficulty producing saliva. So our device is going to collect all of this sample and directly transfer it into the diagnostic cartridge.
Would there be any issue with like patients that have like severe dry mouth, have like different viscosities about saliva? Could that affect how the capillary action works?
No, because our device intends to collect a really low amount of saliva.
And then my last question was, have you guys considered what the packaging of something like this would look like to ensure it maintaining it, I think, sterile or, keeping it safe for the patient?
We haven't accounted for that, but that's for future work. And those bags where syringes come that are like paper bags and they have like the clear film, that's what we can think about this.
Perfect, thank you.
All right. I now call team number 9 to the stage. Team number 9. Aerosol Assist Pro. An aerosol reduction device for pathogen mitigation. Faculty mentor Dr. Mora. Alumni mentor Alejandro Viana. The project is sponsored by WB Engineering. The project is managed by Linda Ordaz. Team members Jim Tuitt, Ebenezer Romero, Cecilia Santaella, and Renee Rukimbira.
Good morning, everyone. We are Team 9. My name is Epinice. We have Linda Ordaz, Renee Rickenburn, Jayla Tu, and Cecilia Sampaella. And today, and our sponsors are W Engineering. We'll be presenting our senior design project, the Aerosol Assist Pro, an aerosol reduction device for pathogen mitigation. Every day, dental professionals are exposed to this invisible threat, known as aerosol particles. They can't see it, they can't feel it, but they are most definitely breathing it in. These aerosol particles are generated by using high-speed instruments such as ultrasonic scaling, drilling, as well as air polishing. Since these particles can remain airborne for such an extended amount of time and can carry viral bacterial such as bacterial, fungi, or viruses such as respiratory pathogens such as influenza and COVID-19, this poses a health risk for dentists, hygienists, as well as the assistants. The COVID-19 pandemic brought significant attention to aerosol-generating procedures. Although clinicians responded by increasing the use of PPE, HEPA filtration, and HVAC systems, they are bulky or they don't capture the aerosol particles at the source. This leaves a gap for a device that captures aerosol particles at the source and is hands-free. When designing our prototype, we focused on 6 key design properties. We wanted to ensure that we maximize aerosol capture while ensuring the device is low in noise and integrates seamlessly with the existing HVAC systems. We also took into account patient comfort as well as the device making sure it's able to be sterilized through the existing autoclavable procedures, as well as no assistance required so you're in and out of that dental room. When developing our design, we focused on 3 key components. The aerosol inlet to ensure maximum capture, the saliva ejector placement for ease of use for the dental professionals, as well as the connection point to ensure secure fit as well as manufacturability. This is our solution, the Aerosol Assist Pro. It is a hands-free, reusable device that integrates seamlessly with the already existing HVAC systems. And I'll pass it over to Jayla to discuss the clinical impacts.
Thank you. Aerosol Assist Pro improves safety and workflow in the dentist's office. The device integrates with standard HVAC systems. Its hands-free design makes it easier for the clinician to focus on what matters the most, the patient. Our device enters a rapidly growing market. According to Market Insights report, global dental suction device market is valued at $515 million today and is projected to market at $1 billion by 2035 with an annual growth rate of 8.9%. North America market share stands as the largest regional market, making it a target starting point for commercialization. Because our device integrates easily with standard dental practices, its cost efficiency and its simple design makes it adaptable for developing and developed communities. Because it requires minimal training, it will support global efforts to reduce the transmission of airborne diseases during dental procedures. When we evaluate existing aerosol control methods, every solution had a trade-off. Some improved safety but disrupted workflow. Others were affordable but provided limited aerosol assist. Our device is affordable, reusable, and effective in the workflow, and it's portable. Therefore, it's easy to be used in dental practices, and it's perfectly integrated into dental systems, making it an ideal solution. Our engineering requirement was driven by clinical need. Our primary goal was to reduce 90% of aerosol exposure of particles smaller than 5 micrometers, preserve the dentist's view, reduce noise to 75 decibels, and making sure the device doesn't collapse under suction while not blocking the patient's airway and following biocompatible standards making the material silicone medical grade. I will now move it on to Linda with our simulations.
Thank you, Jayla. So the first simulation we performed was a fluid flow analysis. Our results showed continuous airflow from the vacuum inlet to the HVA outlet with no flow reversal. As the air passed through the bottom of the device, the velocity increased from 0 to 0.25 meters per second. This simulation confirmed that our device provides stable and efficient internal flow. The next simulation we ran was a thermal analysis. The results show that the device reached the required sterilization temperature of 121 degrees Celsius with a uniform temperature distribution, indicating that the device is able to withstand the autoclave process without experiencing any temperature variations. The third simulation that we performed was an equivalent stress analysis. The maximum bond mission stress was 40.8 megapascals. Since this value is below the yield strength of the material, the device is not expected to fail under normal operating conditions. For our factor of safety analysis, the calculated value was 1.60, meaning that the device maintains its structural integrity while in use. And now I will pass it to Cecilia for our verification test.
For our first verification test, we wanted to evaluate airflow velocity. This was done by taking several measurements under identical conditions using an anemometer. The previous device, we measured an approximate of 196.8 feet per minute. And our aerosol Pro, we measured an approximate of 295.3 feet per minute, showing an approximate 50% increase in airflow velocity. This increase will enhance aerosol capture. For sound level measurements, we used a sound meter. The previous device ranged between 82 and 85 dB SPL, while our aerosol Pro ranged between 72 and 74 dB SPL. The 10 decibel reduction will make the use more comfortable for both the patients and dentists. For the drop test, we wanted to evaluate durability. This was done by dropping the device 3 consecutive times from the height of a dental chair, which is about 3 feet. After each test, we checked for visible damage or loss of functionality, and none were observed. We also had to make sure that the patient's airway is not being obstructed by the device. This was done by taking measurements with calipers from the airway all the way to the cheek retractor. We measured a 5 centimeter gap, which is a big enough gap to not cause any gag reflexes or obstruction. For the field of view, we had to make sure that the dentist had a clear field of view without the device obstructing it. This was done by taking caliper measurements before and after placing the device into the patient's mouth. After several measurements, we found a range of 48 millimeters. This is also verified through clinician evaluation. Lastly, we also had to make sure that the vacuum inlet was stable. This was done by taking caliper measurements before, after, and during simulated testing conditions for 30 minutes. Our results showed no change in the vacuum inlet size, meaning that it does not collapse on itself or close during suction, allowing for aerosol capture. I'll now pass it down to Renee with regulations and standards.
Thank you. Our device is built on a foundation of strong regulatory alignment, engineering rigor, and a clear understanding of the existing intellectual property landscape. Because it functions as a dental aerosol assist system, it falls under the FDA Class II medical device category, which defines the regulatory path that you must follow, which includes identifying a predicate device, implementing design controls, completing verification testing, and preparing a 510K submission for FDA review and clearance, which is followed up by registration, listing, and quality system compliance. To support this pathway, our engineering framework integrates key ISO standards. For example, we have ISO 14901, which is for aerosol risk-related management. We have ISO 10637, which is for suction system performance. And we have ISO 17665, which is for steam sterilization of usable components. Cost efficiency is another major advantage of our device, as low-cost liquid silicone rubber and polycarbonate provide durable and biocompatible construction, while our autoclavable and reusable design reduces chemical waste and lowers long-term procedure costs, even in small batch production. Our pattern search shows that while existing devices focuses on suction currents and cheap retractors of aerosol channels, none combine external aerosol capture with ergonomic and hands-free assistance the way our system does, reinforcing its clinical relevance. And now Linda will talk about the accomplishments of our device.
Thank you, Renee. So to summarize our accomplishments, we successfully designed and built a reusable aerosol capture device that integrates with existing dental equipment. We focus on improving patient comfort, reducing noise levels, and ensuring that the aerosols captured are effectively directed towards the HVE system. For our future work, there are multiple opportunities to improve the Aerosol Assist Pro. First, we plan to integrate a bite lock to provide additional patient stability during dental procedures, and also incorporate a built-in mouth retractor to improve accessibility and reduce the need for additional dental instruments. We would like to thank our professors and our sponsors for their guidance and support, and thank you to everyone for being here today. So we will now accept any questions.
Great job, Team 9. I think it's a good product to be used, and it fits a need. My question is, what is the weight of the product? Because right now, from my experience, it's just the irrigation tube, but now you're adding another device that's going to sit inside of a patient's mouth for a long period of time. So for patient comfortability and usability, how much does it weigh? And was that something that you considered in your research?
Thank you for your question. The device weighs 40 grams, and we chose also to make it more comfortable since we know that we don't want anything hanging from the patient's mouth for it to be uncomfortable. That's why it's made out of medical grade silicone. Like that, it just sits well on the cheek and doesn't cause any lesions.
Great job. Was there any consideration given to different dental procedures, how this device will work in different dental procedures?
Well, depending on the different types of dental procedures, the cheek retractor is made like that the dentist can move it from side to side, like that they have a full view of the patient's mouth. And also depending on what position they want the saliva ejector, if it's interfering with what procedure they're doing, they can fit the saliva ejector to put it in more in the device to make it shorter or to make it longer, depending on where it's needed during procedures.
Thank you, Team 9. I like that this impacts the actual clinicians and the dental hygienists. We often think of medical devices for the patients, but it's also, everybody else in that room. Did you guys look at the material and how through time, maybe the autoclave process can affect the material or, the performance of the product?
Yes, we did several simulations, and the material can withstand the heat that the autoclave provides. And also the device fits into different types of sterilization machines that are provided in all dental offices.
And then how well does your product integrate with different types of suctions from different models and brands? Is it pretty standard?
It integrates with the standard saliva ejectors, and it integrates perfectly with the HVE, which is standard for all dental offices.
Thank you.
Okay, let's give it up for Team 9. And now call team number 10 to the stage. Team number 10. Affordable bioelectric prosthetic hands for functional grasping. Faculty mentor Dr. Raj, alumni mentor Deuce Odrasmi, project sponsor Bioengineering Labs. The project is managed by Emily Iriarte. Team members Alyssa Eliason, Jalen Ford, and Juan Vasquez. Let's give it up for for team number 10.
Good morning, everyone. Welcome to Team 10's new design presentation. My name is Alisa Yasin, and I'm joined by my teammate, Emily Diarte, Juan Vasquez, and Jimmy Ford. Today, we'd like to take you on the journey of an affordable myoelectric prosthetic hand for functional prosthetic. Let's start with this picture. As you take a look at it, imagine struggling to perform the simple task of opening a water bottle. Looking at the bigger picture, she represents one of the 57 million people worldwide living with a limb loss. When a simple task of opening a water bottle requires adaptation, losing a hand doesn't only change how somebody interacts with the world, it also changes how they see themselves, leaving millions of people experiencing a low self-esteem, anxiety, and depression. As engineers, we can't restore what was lost, but we can design technology that helps restore functionality, independence, and confidence. The challenge is that current myoelectric prosthetic hand users are forced to choose between functionality and affordability, because highly functional devices are very expensive, while more affordable ones require compromises, such as repositioning the thumb. The literature reflects this challenge when 81% of users report functionality and 74% of users report cost as key barriers to prosthetic use. In order to address this global challenge, we design and improve the thumb mobility in a standard myoelectric prosthetic hand, enabling different grasp patterns, while keeping it simple and affordable, manufacturable to 3D printing, and this will allow our hand to be used in diverse communities. Now I'll pass it to Emily to talk about design development.
Thank you, Alyssa. So with functionality and affordability as our top priorities, we started designing each of the subsystems for our prosthetic hand. We began with the thumb. So we followed a design concept process, with the first one being the flexible hinge, then we moved on to a ball socket joint, and finally we settled on a captured hinge joint. This one allowed us to have controlled and repeatable flexion, as well as clean motor integration. We then moved on to the tendon system, where our first design concept was the torsion spring system. We then moved on to dual non-elastic system, and finally we settled on a non-elastic system, non-elastic tendon for flexion and elastic tendon for extension. This allowed us to have reduced servo load as well as smoother movements of the fingers. Both of these components integrate into our full hand assembly. Our hand is controlled by muscle flexion patterns. For example, 1 flexion equals power grasp and 2 flexions equals release. So this is controlled by our electronic design, which is based around our custom PCB, which was built around an Arduino Nano. Our circuitry is able to regulate our LiPo battery power, as well as regulate LiPo battery power, as well as process EMG signals from our middleware, as well as has designated connectors for our servo motors. This was able to minimize any unnecessary wiring, as well as improve the stability of our circuitry. So all of these components fit into our compact design, and now begs the question, how does our design help the user? Now, Juan will answer.
Thank you. And to answer that question, the clinical impact of our device comes from its ability to restore essential hand function through multiple grasp patterns and thumb opposition. Our hand is designed to improve dexterity, promote independence, and enhance quality of life for those with upper limb loss. And it doesn't just address a clinical need, but a big gap in the market, as there's a growing demand for myoelectric prosthetics to be affordable, yet many of them are extremely expensive. So our goal is to provide comparable functionality at a lower cost. And to determine where we could provide the greatest value in the market, we evaluated several commercially available prosthetics, beginning with the simpler non-multi-articulating devices such as the Armach Myo Hand and Griefer. And while these are reliable and durable, they sacrifice dexterity, grasp versatility, or they require manual thumb repositioning. So these limitations highlighted opportunities for us to improve functionality. And then we compared those with the more advanced multi-articulating devices, such as the iLimb and the Hero Arm. And while these do have great dexterity and have multiple grasp patterns, they are of course extremely expensive, require a lot of user training, and are complex mechanically. So these comparisons led us to our design inputs, and using our market research and benchmark results, we translated the user needs into measurable requirements. So our hand is designed to grasp objects up to 0.5 kilograms, with about 13 newtons of grip force while still maintaining velocity of view response, user safety, and natural joint motion. And this is the criteria we'll use to verify during testing. And I'll pass it off to Jay to discuss simulations.
Thank you, Juan. So before we begin building our project, we wanted to verify if our main components were strong enough to handle everyday use. Therefore, we decided to run stress simulations on both the palm and forearm socket, and we found that both stayed well below their material strength yield limit. Moving on, we also decided to look at how these components would bend or flex under those same loads. And in this test, we found that they both showed less than 1/10 of a millimeter of displacement, showcasing the design's overall ability to maintain its shape while in use. Moving on, we also decided to calculate the factor of safety in order to see how much the design could handle past what is expected to experience. We found that both components had a factor of safety greater than 1, indicating and showing that the design's overall reliability. Since the fingers move every time the device is in use, we decided to test one of the fingers in a worst case bending simulation, and even in this scenario, we found that the finger was able to maintain its shape while also staying below its material strength yield limit as well. We also decided to test the tendon materials, which consist of the fishing line and elastic cord, and with that, we found that they were both able to handle repeated loading while also staying below their material strength yield limit as well. And finally, we verified the electrical system by analyzing the buck converter. We found that the buck converter was able to safely lower the voltage that was to be supplied to the MyWord and Arduino sensor. And with that, we verified and concluded that our entire system operates within safe electrical limits. And now I'll pass it over to Alyssa to go over our roadmap.
Each stage of development contributed to our final prototype. As we transition into verification testing, at the corner of each slide will be a section of the roadmap. Our first test is the grip force test. A precedent gate is not functional if you can securely hold and grasp everyday object. We wanted to have a maximum grip force between 12 to 14 Newton, and we're able to verify that by being able to hold an object up to 0.9 kilogram with a force of 12 Newton. Grip force alone cannot demonstrate functionality. Thus, we wanted to make sure that our precedent can grasp and hold different objects of different shape, especially delicate items, for example, a raw egg. Ultimately, the goal is to restore independence by being able to grasp and pitch everyday objects, for example, pitching a fork or grabbing a phone. Our next step is a static friction test. Our goal was to have a static friction of 0.6. We performed an incline test, and the silicone represents the silicone surface, and the PLA block represents a smooth surface with negligible static friction. And with that, we were able to verify that our hand is able to grab with an angle of 36 degrees and a coefficient of static friction of 0.733. Now I'll pass it to one to discuss more testing.
So our next verification test, we evaluated the total assembly weight, and across 10 trials, we found that it was about 874 grams, which did meet our design requirement of keeping it below 1 kg. And then next, we verified the joint angles for the thumb and the finger joints, and we did that by using a digital jointometer. And all the measured joint angles fell within the specified acceptance criteria, which we took from anatomical literature, and that essentially confirms that the prosthetic achieves the desired motion. And then after that, we verified the manufacturing tolerance or the precision of the assembled components, specifically between the thumb and the palm, and that was to ensure a consistent fit and that assembly would be successful. And across the trials, the average clearance was about 1.13 millimeters, which passed our criteria of remaining below 1.5. And then we tested and assessed the electrical system by measuring the voltage regulation and isolation, and all measured voltages in the PCB remained within their expected ranges, and all components received the expected voltage and current. And continuity testing did confirm that user contact surfaces were isolated electrically as well. And we also verified the thermal performance of it during operation, and that was done by monitoring the temperatures of all the electrical components, and they all remained close to room temp with minimal variation, confirming that there's no overheating. And we also tested response time. Our goal was to have response time under 1 second, and so we tested for the power graph specifically, and for closing it was about 0.71 seconds, and for open about 0.64 seconds, which passed our criteria. And I'm gonna pass it on to Emily to continue.
So continuing with response time, we also wanted to test it in different environments, such as the heat and in the cold. In the cold, we witnessed a response time of around 0.67 seconds average, and in the heat, around 0.40 seconds. So we can see that both of our response times all remain under that 1 second criteria. And we also compared it with the room temperature, and we witnessed no % increase across the different temperatures. So moving on to the EMG sensor, as you can see, we verified that rest and command signals have a clear difference, as well as contraction strength showing a strong linearity with an R2 value of around 0.98. We also wanted to make sure that the hand was able to respond correctly with the correct gesture when the user was using it, and we witnessed an overall accuracy of 92%. So moving on to our last verification test, we wanted to verify our tendon system. So we wanted to make sure that both materials were strong as well as durable. And through tensile testing, we first tested the fishing line as well as the elastic cord, and we saw that the strengths that it reached without deforming were above the load that was delivered by the servo motors. We also did cyclic testing on the elastic cord, and after 50 cycles of load, we saw force retention of 94% with no deformation, passing our criteria once more. So now I'll pass it off to Jay to discuss the regulatory.
Thank you, Emily. So we looked at, further in our project, we looked at what would be required for the prosthetic to be classified as a commercial medical device. And we found that it would, based on its motor, software, and electronics, we found that it would most likely be classified as an FDA Class II medical device. Moving on, we've used many established engineering and medical device standards as general guidelines during our development process. By doing this, we're able to keep safety, reliability, and overall design quality in mind. Now, keeping the myoelectric prosthetic hand affordable is one of our main goals. By utilizing 3D printing, cost-effective electronics, and a modular design, we are able to reduce manufacturing costs while also making future repairs and upgrades less expensive. And as also part of our project, we reviewed relevant and existing patents. We did this in order to better understand current technology and make sure our design is not only based on, but also improved upon from existing work. So, in summary, we successfully designed, manufactured, and verified that our portable myoelectric prosthetic hand is capable of functional grasping. Through the verification tests we've been over, we've also made sure that it met its key engineering requirements. And now I'll pass it over to Alyssa.
Thank you, Jay. Features include increasing reach strength, enabling wireless control, integrating individual figure actuation, and implementing force sensor feedback. Thank you so much for joining us on this journey, and we'd like to speak specific to instructor, faculty, sponsor, family, and friends. And if you want to know more about our hand and to watch the video again, you can scan the QR code and look at the website. Thank you.
Good job, guys. So my question is, how does the machine handle crosstalk? Crosstalk. Okay, so crosstalk is if it's looking for electrical signals from one muscle, but it picks up from another muscle.
So we are only looking at we have one EMG sensor in our hand, so we are located in the ulnar side of the forearm, and we made sure how we control our hand is muscle flexion patterns. So for example, the user contracts their muscle once, the hand will close to a power grasp. They do it twice, and it will do a release motion, so it'll open the hand. And we also have other motions, such as if they flex 3 times, they can have a pinch gesture. And if they do a strong contraction, like that we separated with thresholding, so we separated with thresholding, they can do up to a gesture. So like right now, our hand is programmed to do a thumbs up gesture. So for the crosstalk, there wouldn't be any for all the testing we did, there was no miscommunication between the muscles because it only detects like a contraction strength, if that makes sense.
Thank you, Team 10. So how are you guys going to make it more affordable? Is it material? What was the method of trying to make it more affordable to the loss patients?
Yeah, so one of our main things that we did with as far as manufacturing with the hand was we made use of the fact that it was 3D printed and cost-effective electronics like just simple resistors and just some things that you find in normal electronic stores. And also with the 3D printing, the material that's used is really common, PLA. That's basically the whole makeup of it. And also just, as well as we took advantage of, instead of using a circuit board with wires and that type of setup, we took advantage of the fact that PCB in order to save on cost and stuff of that nature.
Okay. And then what, you guys touched on this a little bit, what sort of electrical safety testing would you guys be doing? Like if this went to like mass production?
If this was going into mass production, we'll do current leakage tests to make sure that if the user is using the hand, there's nothing wrong. And as future work, we would like the hand to be waterproof as well, because you might be holding something that is wet, and then that would include electrical safety for those as well.
Thank you. Great job, a lot of work went into this. So I just want to commend y'all on that. I see here that you have silicone tips integrated into the hand. Is that a part of the design? Is it gonna come with the product, or is that something that is not something that's gonna always be with it? That goes into the grip or not?
Yes, that will come with the device.
Okay.
That will support the grip.
Okay, because in the pictures here, it's not there, but here it is. That's what I was asking. And then the other question is, in the design of the thumb position, can you talk me through that process while you have it angled where it is versus somewhere else?
So in order to, one of our main focuses was to be able to do that thumb repositioning, opposition. So many hands struggle with that, depending on how they design that thumb joint. So many hands can only bend somewhat and not fully, or can't fully oppose. So we took advantage of positioning the motor in the palm in order so that we could get both the angle, so the thumb goes slightly upwards, as well as being able to have more strength and power in our grasp.
Also I'll add to say that the motor in the palm also helps with space for the socket, so that when the person is gonna put their hand, there's less in the socket.
Okay, and then when you did the heat testing, was the fish line and the other wiring that's connected to the fingers included in that?
Yes, everything, we did the testing
With
the
everything
vehicle,
inside?
the whole prototype.
Okay, and there was no degradation of the fish line or the other product that's used
No.
over time? Okay.
But if we're mass producing, we can definitely test that more intensely.
Okay, thank you. Team number 10. I now welcome team number 11. Team number 11. Omni Style. Novel adjustable video assist intubation stylus. Mentored by Professor Munir. Alumni mentor is Sefer Luciani. Project is sponsored by JCAT Biomed and is managed by Bianca Aris. Team members Benson, Elsie May, Nitty Johnson, and Amanda Garcia. Let's give them a round of applause.
Hi everyone, my name is Amanda. This is my team, Benson, Bianca, and Nitty, and today we'll be completing a presentation on our device called Omni Stylus. It is sponsored by Jonathan Kanalaika of JCAP Biomed Collaborative, and now we'll be passing it on to Bianca to continue with introductions.
All right, so before getting into our project, we kind of want to go over the airway anatomy. So when you're doing intubation, the goal is to guide the endotracheal tube past the epiglottis, through the vocal cords and into the trachea. Sometimes it can end up in the esophagus, and when that happens, then the patient would get the proper ventilation that they need. And therefore, we believe that proper visualization is so important in this process. So when intubating, there's two common tools that are used. This is the bougie and the stylet. The bougie and stylet are used to guide the endotracheal tube to the trachea when there's difficult airway anatomy. And this is a process that doctors are very familiar with. They know how to use it. They use it commonly when doing this intubation technique. And therefore, when we were doing our design, we wanted to keep that in mind and make sure that this was going to be a practical design and flow with their current work. And so, difficult airways are still a very common issue in airway management. These are examples of this could be blood, swelling, it could be poor visualization, difficult airway anatomies, and with all these difficulties, it can cause multiple attempts. And with each extra attempt, increases the risk of complications. And those are the gaps that we're trying to fill with our project. I'm gonna go ahead and let Nidhi continue with the current modalities.
Thank you, Bianca. So, talking about the current modalities, like the current airway managements like video laryngoscope, direct laryngoscope, they have their own limitations. So they can be of poor visibility, high cost, bulky, and limited maneuverability. These challenges motivated us to the development of OmniStyler, which improves on these limitations. Our goal was to design and fabricate a functional proof of concept device. The final prototype integrated a camera, LED illumination, depth markers into bougie-related device. And as we are in senior design, our main focus was doing on engineering design and verification. So our project addresses both clinical and business needs. Clinically, it helps to improve the visualization and airway management. And from the business perspective, the airway management market is growing. So the existing devices are in a difficult position where they have to be selected from the low cost or the good performance one. So this goal made us to create the OmniStyler, which combines all these features into a simpler and affordable one. With that, I will hand over to Amanda.
Thank you, Nidhi.
So, with all of the information that we had gathered, our proposed solution, we believe, is something that will close the gap within the market. Our goal was to create an adjustable video stylet with real-time visualization, as well as having a continuous rotational maneuverable shaft, and for it to be compatible with multiple size endotracheal tubes, ranging from all the way to pediatrics to an adult. In terms of our market requirements and design inputs, we had a set amount of goals that we wanted to reach, so we created market requirements that were corresponded with a number of design inputs. For example, our main market requirement that I would say would be improving airway visualization, and for that, the design input that we put in place would be creating a miniature camera with an LED illumination, and so on and so forth. In terms of our early design, we have gone through several iterations. Our main concerns was the ergonomic handle to make sure that it's practical in clinical settings. And the different mechanisms that we were using for the adjustability, we went through a number of different ways to create the rotational capabilities. And with all of this in mind, I'm going to pass it on to Bianca to continue with our final design.
All right, thank you, Amanda. So yeah, just like Amanda mentioned, that when we started this design, we initially had it as a set size stylet. This was going to be adjustable, so it was going to adjust to whatever size ET tube that you see here, different lengths. They're all different lengths. We wanted to make sure that it was going to be compatible with all of them. We had this design in set, and then we brought it to a director of a medical training center. She tried it out. It did work. We all believe that it wasn't as practical as in how they currently use it in the clinical setting. And so for that, we decided to move on to more of a bougie style stylet. So this is more of a long shaft, which is of 70 centimeters. It also has the compact proximal housing, which includes the adapter for the ET tube, like she said, it's compatible with pediatrics up to adults, and then it connects to the end, and that way that the shaft that we have would track through the trachea and be able to allow the tube to go and guide into it. And so when we got to this final design, we separated by function. So we have the display and the electronics, and then we have the compact proximal housing, which includes the rotational feature, and then that also has that adapter that I mentioned for the ET tube, and then of course is a shaft with the
camera and the LED. This smaller version and more simpler version was just more functional with the way that the clinical workflow is now. It makes more sense, it worked better, and has a rigid shaft that keeps it stable and allows for this process to work successfully. I'm gonna go ahead and pass it over to Benson so he can go over our simulations.
Thank you, Bianca. So when looking at our simulations and our overall design, what we decided to do was simplify the overall mechanism. When we're looking at our mechanism, it can be simplified to a cantilever at a one fixed endpoint, and under that standing, we are able to create a mathematical model which decreases our variables from the overall length and the diameter of the internal metal core, as well as the final material that we're going to be using that needs to tolerate multiple stresses back and forth. For our gear assembly, we have another simplification here for our assumptions. So each of these have axial symmetry, so we increase stress on each of these, increase the load on each of these 2 to 3 factors above normal human pressure, and showed that each of the initial teeth, the teeth in contact, and the neighboring teeth have within tolerable deformation and enough strain to last many cycles. And the housing itself, its deformation is based on the human pressing at high strength. So we did 55,000 pascals just to see how much failure or how much deformation before this device fails. The internal core is made out of stainless steel 316L. This allows it to have 360 cold drawn 316L, which allows it to have 10 to the 6 cycles before fatigue, failure, or even crack propagation. When looking forward to our electrical components, what we decided to do is borrow some of the inspiration from a borescope assembly. A borescope assembly is a similar use case, but is not modulated to fit the human body, right? So we borrowed the LCD PCB, but for our use, since the individual is constantly straining on the wires, we included a slip ring assembly, which allows it to go up to 300 RPM without deformation, destruction of the wires inside. The PCB and rechargeable battery are able to work for 4 hours on a single charge. However, the actual intubation technique will take 30 seconds to a minute. When we're looking at the camera, it's able to produce a visual live feed under a second of latency, and this allowed the individual intubating to have live feed from the distal end and look into the airway themselves. So when we were manufacturing, what we did was 3D printing. Our models are 3D printed out of PLA. The intended model is to be out of ABS, which has a higher strength factor than that which we printed with. It showed that the device is capable to withstand that. Under our constraints, the 5mm diameter of the intubation tube of the smallest individuals, we were able to select a wire, replace the internal wire from the initial aluminum that was in the borescope to that 316L steel, which allows that bending material, and still within our diameter limit. When we're looking at the, sorry, I tickled my throat. When we were looking at the overall sheathing of it, we removed the polymer and replaced it with a polyolefin polymer that allows it to be inert to the body, waterproof, and allows it to be sterilized, both the internal components and the external, with H2O vaporized. Future manufacturing, we will have to produce a custom PCB to limit the amount of uses or increase the amount of uses depending on what the future individuals would like, as well as prepare the device for a clinical setting. We will give it on to Nidhi to continue our design.
Thank you, Benson. So after our prototype was done, the next step was to do the verification testing. So for the verification testing, we tested our camera like startup time, image quality, shaft radiation, mechanical strength, compatibility, to make sure like with 3 different endotracheal tubes. So and overall we got the successful results, and we were able to conclude that our camera startup time was about 3.31 seconds, and our average video latency was about 0.61 seconds. And after that, we had to do it with our airway trainer, which was a replica for a human trainer. So with that, we were able to get a successful result too. We were able to make sure that there was clear image quality, smooth shaft rotation, and reliable LED illumination. And also at the end, we were also made sure that we were able to get the engineering goals we set in the beginning of our project, and also we made sure that the components were secure in all the positions. With that, I will hand over to Samantha.
Thank you, Nidhi. So in terms of the cost of our device, we had a budget of $500 to work with, and we were able to complete our proof of concept at around $70 with FIU's resource fabrications and repurposing of material that we had. In terms of regulatory assessment, we believe that our device would be classified as a Class 2 medical device, and it would have to go through 510K pre-market notification and pathway. We kept the regulatory assessment in mind as we were designing through our design process. For our engineering standards, there was a number of standards that we applied throughout our design process, to primarily in terms of risk assessment, electrical safety, and in material selection. These are the standards that we had selected and we used. And I'm going to pass it on to Bianca to continue with our global perspective.
Thank you. So intubation is a process that's done all around the world. Our goal was to create a reusable device that would function and naturally blend into the current clinical setting and the flow that they already use. And although this is a proof of concept, we do believe that our project has a foundation to make great advancements and continue in the future. So, like Benson mentioned before, in the future we do plan on switching to medical grade materials. We also would like to have more custom electronics like the LED and the HD camera, rather than the commercial borescope taken apart and put into our project. We also would do all types of testing, including sterilization testing, cadaver testing, clinical testing, all of this that would be necessary to get the FDA approval.
At this time, we'd like to thank all those involved in our support of this project. We'd like to thank Dr. Munir, right here in the crowd, Jonathan Kadalika, our sponsor, and our senior mentor, our alumni mentor, Sophia. This project has been a great improvement in all our lives. Thank you.
Thank you.
Questions from the judges?
Can you set it up how they would use it?
We have the arm, we have our intubation stylus. This is the smallest one, and we're still able to properly push it through.
And that's the pediatric
Yes,
size.
this one. Smallest, and then on the housing right there, we do have this attachment. 1, 2, 3. Live feed. Adjustment of brightness. So that adjusts the LED at the end, which is about 150 lux, which allows for proper visualization within that airway under dark conditions.
Okay. So I know in the future slide, it was about reusability and sterility. Can y'all talk me through, with this LED and this happening go into a patient, how the clinician will be able to make it reusable or keep it sterilized? Do we have to have multiple? Like, just talk me through what you guys are thinking.
Yeah.
Okay. So in usual intubation settings, they do provide a plastic sheet that goes over it just to prevent it from contact with the body, but this is also still waterproof. It will be sterilized with vaporized H2O, so none of the components would perform in that manner.
Great job. I really like that you guys opened up the borescope to take the PCBA from it. So was there a benefit in like any time savings with the traditional methods and with using your camera to be able to intubate it quicker?
In the overall timing, yes. So our main target audience is in an emergency setting, and in those settings, they do not have a video camera. They actually have this right here, which is a direct laryngoscopy. So in your hospitals, not hospitals, but ICU, intensive care unit, the ambulatory care, and also emergency settings, they just have this. So if I were to pull out this dummy here, they are taking this device, cropping the tone, just like there's no camera here because the video laryngoscope has a higher cost and they're usually not affording that, and they're looking with their eyes. They're not able to see this usually if there's a deformity, which is about 90% of the population.
Yeah, it'd be interesting to see like if there's any time savings in getting it successful, right? Using your product versus the traditional methods that they use.
So in those clinical settings, they're looking at more than one attempt, and in our device, we're able to do it in one attempt, which saves you overall time.
And I would say with personal experience, like obviously we're not professionals, we just learned not too long ago how to do this. And personally, doing it took me a couple tries just with the bougie without a camera. And then once I tried it with this, you can literally see the vocal cords, the trachea, and it's super easy to find. Once you get it, you push it in. So I would say it saved me time, it saved them time, but,
And the
you know.
doctor that we worked with, she said that it saved her time. There's a big difference
Yeah.
between using the traditional method compared to our method.
Great job, guys.
Thank you so much.
Thank you.
And that concludes our oral presentations. The lunch will be served over in the Panther Pit. The judges, please retreat to EC 2680. It's in the BME suite.
I'll take it.
Oh, you got it. You'll be escorted. And there you can take your accoutrements. Yeah, you come back here. And please check your schedules. At 1 p.m. is the poster presentation right adjacent to Panther. Thank you very much. And you guys. Thanks for coming.
And it's extreme.
Room service coming. Are you,
And the sterilization for me is expected. They literally have set up for 200 patients, so that was expected.
Guys, we did it!
We're like almost there.